이거구나.
이거요?
말해봐요.
hello. 절로 나가면.
거기서. Can you hear us? Are you there? 딴 데 갔나 봐.
그럴 수도 있을 것 같아. 아무도 없으면
이거 디스플레이 설정을 바꿔야겠다. 수학이 아니라 이거 어떻게 해야 되나? 시작하시죠. 네, 다 됐어요.
얘기하고 있습니다.
Yeah. One, two. Okay. Good morning, everyone. Thank you for coming. And we are just gonna start right now. And first of all, thank you for attending our workshop today. This is really early morning, and we will start right now. And we will start with opening remark from Kyungmoo Lee. He's a professor of Seoul National University and also excuse me. So please welcome Kyungmoo Lee. So he's one of the main organizers of our workshop.
Okay, good morning, everyone. Welcome to the 2023 NICE workshop here in Vancouver, Canada. I'm Kyungmoo Lee from Seoul National University, and I'm one of the co-chairs of this workshop. And I'm very glad to meet you all at this meaningful, gathering today. Okay. As you know, currently, the world is fascinated with the ChatGPT and generative models. Okay, new research based on the foundation models are trained on, unimaginably large, scale of data set, is producing astonishing result in these days. So, in addition to the language models, the field of computer vision is also witnessing, emergence of various types of, generative models, including the DALL-E from, OpenAI and Flamenco from DeepMind. Okay, those are actually started with the generating, images, but later expand into, scene understanding, enabling the various forms of scene comprehension. Okay, so actually, this workshop aims to discuss image captioning, which involves communicating in human languages in terms of, in the perspective of the scene understanding. Okay, so traditional closed set image captioning, limited by constrained data set, has several limitations. However, a recent advancement in self-supervised learning actually brought attention to zero-shot image captioning. Actually, where the models are trained on large scale of data, trained on actually the unlabeled data set, do not rely on specific data set. So actually this workshop tried to evaluate the current state of the image capturing models and explore diverse methods for effective image captioning. Okay, in conjunction with this workshop, we launched a challenge on zero-shot image captioning over the last 3 months, with the new data set, very large data set with very high resolution images provided with the LG AI research and Shutterstock. Thank you very much. Okay, so the aim of the challenge is to evaluate the current state of the zero-shot imaging captioning models, and also explore the further research directions or ideas, something like that. So this workshop includes the presentations from the challenge winners, and they will share their ideas and how they achieved outstanding performance. Okay. Furthermore, we have gathered a group of diverse, attendees from both academia and industry. So, and also experts in image captioning evaluation and social bias and large-scale data set and relevant fields will deliver excellent invited talk today. Okay, so and they will, discuss on the limitations of current captioning, image captioning, issues, and also the future direction to zero-shot image captioning. Okay, so I'd like to thank all the committee members, organizing committee members who have, put a lot of effort to set up this workshop and challenge, and also the sponsors, LG AI Research and Shutterstock, and also the invited speakers and challenge participants, and all the the attendees here. Okay, so I hope that everyone will gain the valuable insight from this event. So please enjoy. Thank you very much.
Now we're gonna do the award ceremony for our nice workshop challenge. So please welcome. Please welcome the first winner and the. Yeah. Please welcome the first winner of the first place. First place is from Uri Bank, from Korea, and we first tried to split the track into two, because we first expected that students will have a hard time during the challenge because of the limit of the resource data and the hardwares, all those stuffs. But we actually, in the result, they actually, students got the first and second place, because there was a, well, we didn't, okay, there was some, well, we first thought that there will be, the zero-shot image captioning will need large set of data and too many GPUs, but the students actually found a way out to do the efficient trainings and efficient inference for the models. And actually in the result, the students got the first and second place. So the third place is also from Korea, Kakao Brain. And please welcome the third place winners from Kakao Brain. And second place winner is from KAIST, also from Korea. Please welcome the second place winners. And for the first place winners are from China, but they couldn't come to our workshop because of their visa problems, but they attended this workshop by Zoom. So please give a round of applause so that they can hear us. Yeah, well, due to the network problem, maybe. Yeah.
Of their award, we'll send their award. Later.
Yeah.
Hello.
'Cause-
Hello.
First,
Hello.
oh, can you hear us?
Hello. Yeah. I can hear you, but I can't see you in Zoom. The screen of the Zoom is shows CVPR Alliance workshop, but I can't see you.
Yeah.
Well done.
Please give a talk later.
Mm,
Yeah. Well, we'll reconnect you when it's your time to give the talk. And the next step will be talks from our organizers, and we will cover how we generated all the test sets, and we also gonna talk about the results and what we learned from the workshop, the challenge, and how the challenges goes, and all those things like that. So the first please welcome Alessandra Sara from Shutterstock, and she's gonna talk about how we gathered all the test sets and how we think about zero-shot image captioning, and also how we think about zero-shot image generations and all those stuffs.
Thank you, Daewon. Do you hear me? Do I need to say here? Okay. Let's see if we have the slides up. Very good, very good. So welcome, everyone. We're really delighted to have you here today, and hopefully a few more coming. So today we'll talk about, don't worry, okay. We'll talk about a couple of important things, but first of all, a very brief introduction. Besides the business title, I'm a researcher at the core. I started my career in university. I spent 8.5 years at Bell Labs. And therefore, being here today with you, it's very important to me to continue to have this discussion with students and help all of you to bring those ideas into everything that we do in any company that we work. So Shutterstock is not new with the AI. We launched Shutterstock.ai a few years ago. Before that, we hired an amazing team of PhD from everywhere around the world to help us to develop computer vision research and all other AI project that we run. Guys, come in. We are just getting started. So welcome. Welcome to this workshop. As you may know, we have run a challenge. Many of you have participated. And today we want to talk about how those data are coming to our research. So Shutterstock has a library of 400 million images, 30 million videos, 3D object, editorial content. And what we care about is data quality. Sometimes we use practices that are good for our research purposes. We need data to train our model. But fundamentally, what's the quality of those data? The new model that we are building, it's not like a few years ago where we needed only a few 100,000 of data points and we could build our model. Today, we are looking for millions and billions data sets. And when you have this magnitude of data, then the question is, how do we systematically inspect for quality? And let's be clear, this is our society and our problems on how we're building a technology that is going to impact all of us. AI is everywhere, is in everywhere we do. With chatbot is at the fingertip of everyone, but intrinsically influence our decision and our intimate thoughts. So the question is, when you do train those models, please join. There are many spots here. We are talking about the importance of quality of data and how we collect those data sets. Quality is fundamental to the goal that we want to achieve and the kind of model that we want to bring to our society. Thinking about representation, thinking about diversity, it's not just a checkbox. It's an important aspect of what we are and what we should be doing. So the data set that we collected for this specific challenge was diverse and trying to challenge you to see how many of you were really looking into those data and see the diversity that we brought there, if it was diverse enough. Really challenge your ability to investigate deeper. So we collected 26,000 images. We divided in two sets, the validation set and the final test set. Caption for each image was provided together with a set of keywords. And by the way, this data is still available. If you haven't participated to our challenge, there is still time to join us. The data set was obviously moderated for speech height. Image resolution was 500 pixel and a variety of content, which I will describe it next. What kind of categories did we cover? Did you see it? Did you explore deeply enough where you had data and where you didn't have enough data? Would you expect the same quality of your inference on those less represented buckets? So we add outdoor, largely dominating our data set. And why? Because in outdoor, you have images of many kinds covering a very broad conceptual spaces. A little bit of composition of image, indoor, office, electronics, food, medical, animal, and stocky images. But let's talk about diversity, right? Look around you. We need to constantly challenge, are we diverse enough in our thinking and in everything that we do? Because if I work with people that think like me, we have the same assumption, we have the same biases. We build models that are good for a very small portion of this society. And by the way, company, they want to be international. They want to sell everywhere in the world, and they want to sell to female, to men, and to any other gender. So you need to have every minority in mind when you design model and product. Otherwise, you're only selling to people like you. So we had a data set that in 73% had people on it, the most critical and delicate dimension to inspect. Most of them Caucasian, as in every other data set that you find out there, it's usually much higher than that percentage. And then African American and Asian as the top three categories, and then a representation of everything else around the world. But look the percentage. Did you see that in the data? Did you take the time to explore and understand where you had overrepresentation or underrepresentation? So in our society, we have these unsolved inequalities, biases, stereotype, discrimination, which we discovered a few years ago when we were working on face recognition. I don't know if you are too young to remember, but that was our first shock when we realized our model didn't recognize Black people at all. Forget about women in those categories. And do we believe we have improved from there? No. What are we doing? How are we pushing our society forward with you, the best brain out there today in the generative AI space? Again, and again, the same issue. Representation of minority is nowhere to be seen. So I'm also the co-chair of the UNESCO Women for Ethical AI, which is very simply a way to push forward the recommendation for ethical AI that UNESCO launched 2 years ago and make it real, make it practical. We have to audit the data that we use. We have to audit our assumption and bring those to our research and to our product development. So put human first. Your research, you want your research to be read from every person that is that interest in the world, not only for people like you, from female professor, from Black professor, from men professors. So think that your research has to be representative. Your product, you want to sell your product everywhere in the world. When you go and work for the big company, they don't want to work and sell their product only in one country or in one sector. They want to be worldwide winner. Think about diversity in everything you do. So audit the process, the data and assumption, work with people that are different from you, and be transparent in everything that you do. It'll help us to question our assumption and to help each other to mitigate some of those issues that we hadn't seen in the past. Thank you.
Please give a large thank again for Alexander Sara. And the next will be Seung Hwan Kim from LG AI Research, and he's gonna talk about the the challenge result.
Seung Kim from LGI Research, and I'm in charge of computer vision research at LGI Research. In this session, I will talk about the challenge that we hosted for 3 months earlier this year and share the results. The talk is going to include review of the challenge, trends in the method of top scoring entries, and some insights and future plans for the organization of the next challenge. Our project, named New Frontiers for Zero-Shot Image Captioning Evaluation, is intended to evaluate current image captioning models on a new challenging dataset and find out the achievements and limitations of various approaches. In the project, we have built a high-quality dataset for image captioning evaluation with images and metadata provided by Shutterstock, and organized the challenge using the dataset. The workshop opens discussion on a variety of topics, including the dataset and the challenge and vision language tasks beyond the project. In this session, I will share the details of the first challenge that we hosted this year. The challenge was arranged based on zero-shot image captioning task in order to test the limits of the general knowledge that the current vision language model have. The reason that we choose image captioning as target task is that it can bridge the gap between two different domains, image and text, by enabling language-based image search, automatic image description generation, and language-based image explanation for the visually impaired people. To make image captioning models more useful, they must be able to recognize objects from various domains, even unseen ones, based on general knowledge. Recently, emerging large language models show ability to perform various tasks without fine-tuning on each of them. And researchers in computer vision community are also working on vision models that deal with new data in zero-shot settings. However, current vision models show limits in performing general vision tasks on novel objects or properly describing unseen objects in language. Earlier benchmarks of paired image text data have provided collection of image and corresponding description that follow an instruction. In MS COCO dataset, researchers collected captions in the style that specify category and behavior of main object, while in Visual Genome, relationship among objects in the image were explicitly represented as scene graphs. Image captioning on novel objects was attempted with no-caps benchmark, which intended to challenge image captioning models with unseen or rare object categories. Later, benchmarks of large scale, such as conceptual captions, provided researchers with raw text collected from the web along with each image. This type of image large web crawl data sets put new challenge on the vision language training that originates from the noise nature of the data. More recently, data sets of orders of magnitude large scale have emerged. For example, 5 billion image text pairs in Lion, which provide image URL and corresponding alt texts. Thus, these data sets requires various post-processing methods such as filtering based on image text similarity, watermark detection results, NSFW classification results, and so on. In this challenge, we arranged validation and test data using images and descriptions provided by Shutterstock. We did not provide a fixed set of training data in order to evaluate image captioning models in zero-shot manner, as in no-caps benchmark. The data set includes various concepts in the image, such as high diversity of backgrounds, objects, and relationship between among the objects. Furthermore, captions contain a lot of information on the objects and background of the image, sometimes including name of the specific objects or locations. Thus, we expected the image captioning models trained on general data set to face a lot of difficulties in generating captions similarly to the ground truth. The challenge was held for 3 months, from February to April, and the test images were released about a month before the submission deadline. There were 51 teams that participated in the validation phase, and 31 out of 51 teams participated in the test phase. The top ranking entries in each stage showed CIDR score of approximately 105 and 325 respectively. We assume that the reason of this scoring, this score gap happened due to the ability of the reference data, which has been the role of validation data in the test phase. More technical details on the ways to utilize each set of data will be discussed in the following slides. Now, we present the results of the challenge. As announced in the award ceremony, the top 4 participants were awarded, and the top 2 entries will be introduced in the presentation after this one. As you can see in the table, there are a lot of teams from academic institutions in the top rankings, including the 1st and 2nd place winners. We believe that the impact of difference in available computation power between academia and industry is lessened by using open source large-scale pre-training models. From now on, we present summary of the common approaches that top scoring entries took. The baseline models used by top scoring entries include OFA, BLIP2, and CLIP encoders. There are all transformer-based image or language encoders or architectures used in large language models. In the initial training process, most Most participants use models that are already trained on large-scale dataset. As training datasets, participants use a variety of data for training, including Lion, conceptual captions, and COIO, all of which are publicly open large-scale web-crawled image text dataset. Furthermore, with information that the NICE dataset is provided by Shutterstock, some participants attempted to crawl data from Shutterstock or use a subset of image crawled from dataset Shutterstock website. We are going to share our analysis on the trends that we found among the top scoring entries. First, there were many entries that used custom data curation process for training and fine-tuning. For the data curation, the simplest way was URL-based crawling from Shutterstock website. Some participants use similarity-based retrieval to collect image text pairs that are close to the validation or test data. To measure similarity between NICE data and public web data, participants use clip or blip to extract image or text embeddings, and then calculated similarity between NICE data and Lion or COIO dataset. Text-to-text retrieval using FAISS was another method to efficiently collect similar data for large-scale datasets. The retrieval-based data collection was applied not only to the curation of training data, but also to build the reference dataset for the inference. Top scoring entries show a variety of ways to produce the final captions for the input image with the aid of reference data. For example, one of the teams attempted to prompt similar captions as reference input, and another team chose to fuse captions of retrieval images in the feature space. A few teams used the difference method, for example, the ensemble method, which chooses predictions with higher consensus with captions of similar images. Now we share the overall analysis of the challenging entries and plans for the next challenge. During the challenge this year, few participants seem to directly perform pre-training, while most entries initially use models that have been pre-trained on large-scale dataset. This led to small difference in the total consumption cost required by each team, which consistently resulted in integration of two separate tracks. Next, since we opened the ground truth validation data and the source of the test image, participants curated dataset based on similarity search. Also during inference, similar data was used as reference that could assist models to generate description in the style of test data. This year, we hosted the first challenge in the project, and the submission period was quite short due to the workshop schedule. So we decided to provide the participants with more information on the data used in evaluation, and thus we made validation data open to the public. We think that this policy led to top scoring entries to incorporate approaches that does not fit to the task of zero-shot image caption. Thus, we plan to organize the challenge in which we can test the truth limits of image captioning models with their abilities to recognize captions. Therefore, the next challenge targets to evaluate image captioning models in zero-shot manners. We are now considering several ways to achieve this, including collection of captions in a large variety of styles, including description by people of different backgrounds. Generating captions with AI is also an efficient way if human annotators could refine the caption in shorter time. Furthermore, we will consider organizing the challenge on two different target tasks, one as in the challenge this year, and the other one being more focused on explaining novel concepts. Sorry. We are planning to make the next workshop and the challenging richer in terms of topics and outputs. Thus, we might adjust the challenging schedule so that we can finish it about a month earlier in order to make papers publication possible in the CVPR proceedings. Please be on the lookout on our website, social media of LGI Research, or the workshop website. Once more, we appreciate all the participants of the challenge, and we will attempt to make the challenge more meaningful for the improvement of vision language models. Also, congratulations to award winners. As I mentioned during the talk, the following presentation will be given by the first and second place winners of the challenge. Thank you for your attention. Yeah. Next speaker is Xiangyu Wu. He is from Nanjing University of Science Technology. The title of talk is New Frontiers for Zero-shot Image Captioning, or the same of our workshop. Yeah. Please, Xiangyu Wu, can you hear?
Hey, can you hear me and
Yeah,
see
can
my
you start,
screen?
please? Yeah.
Yeah, okay, I'm starting now. Hello, everyone. I am from Nanjing University of Science and Technology in China. It was a great honor that our team won the first place in New France for zero-shot image caption challenge. Here, I would like to share our solution for this competition. I will introduce our solution in 4 sections: the competition task, our method, implementation details, and the final results. This competition task is similar to traditional zero-shot image caption, whose difference is that a traditional task always includes common objects such as animals, plants, and furniture, while this competition task includes a large variety of visual concepts from many domains and various imaging types. Therefore, it is crucial and feasible that learn aligned range and language representations from large-scale web code data and transfer knowledge from pre-training model to downstream task. Our method is based on the OFA range language pre-training model. So let me introduce the OFA first. OFA is a large multi-model pre-training method that transforms the all pre-training tasks into test generation. So all pre-training tasks can be performed by only one decoder module. For example, VG, visual grounding task, construct the template, which region does the test, man in right shirt describe. Bounding box coordinates are generated by the decoder module. ITM, image test match task, construct the template, does the imaging describe 2 boys playing frisbee on the grass? Yes or no is generated by the same decoder module. It can be seen that the imaging caption task can also construct such a template. What does the imaging describe? And treat it as an encoder-decoder structure. Furthermore, additional information can be added to enrich the content of the template. Therefore, we use OFA as our best model. to perform zero-shot image captioning task. This figure shows the overall framework of our solution. The upper of this figure represents the external dataset we used, line 5B. Each data sample includes 4 information: image, test, URL, and similarity. The lower of this figure represents the 3 parts of model training: pre-training, cross-training, and fine-tuning. In the pre-training part, we collect a pre-training dataset based on specific URL. During the cross-training and fine-tuning parts, we use the clip retrieval library to perform image retrieval to collect training data. In addition, at the bottom of this figure, we incorporate 3 strategies: concurrent learning, similarity bucket, and retrieval augmentation into the 3 model training parts. Finally, we obtain the final prediction result through model ensemble. Next, I will introduce the external dataset line 5B, the 3 strategies, and the 3 parts of model training respectively. For this competition, all of our external training data is collected from line 5B, which is a dataset containing 5.80 billion image test pairs. Each sample in this dataset includes 6 metadata: unique ID, URL, representing the URL address of the image; test, representing the caption of the sample; similarity, representing the similarity between the image and the test, calculated by clip model; and the height and the width of the image. During the competition, we use 2 ways to collect the external dataset. The first way is to directly collect data based on the URL of the images. And the second way is to retrieve similar samples through image retrieval task. Now, let me introduce the 3 strategies in detail. The OFI model is based on an encoder-decoder architecture and does not contain concurrent learning to align image and test. So we add concurrent learning pre-training objective and align new visual concepts through a large number of image test pairs we collected. We found that the competition dataset and the several specific URL data are quite similar. They both contain many new visual concepts as well as new entity nodes in the test. Therefore, during the pre-training stage, we collect 6 million image test pairs through specific URL and perform the data cleaning, such as filtering out too long or short image test pairs, and finally retain the 1 million image test pairs. Concurrent learning aims to learn better unimodal representations before fusion. In addition, we follow LBF and use the monitor model to generate pixel targets as additional supervision. The second strategy is similarity bucket, which provides different similarity prompts to the range language model in the pre-training, cross-training, and fine-tuning paths, as shown in this figure. First, we use foreign clip model to predict the similarity between image and the test. Then we split n buckets from high to low similarity. The first bucket indicates that the similarity and the quality of the image test pair are lowest, and the last bucket are highest. Finally, each bucket is represented by a specific prompt, such as noise, low quality, high quality, and the best match. In the training part, each image test pair belongs to only one bucket. Therefore, each image test pair corresponds to a certain similarity prompt. We insert this similarity prompt information into the template of the OFM model, writing in the template, what does the image describe? The bucket I caption is. Through this similarity prompt, the model can learn the representation of data with different quantities. In the inference part, we fix the similarity prompt to the n bucket and control the model to generate the most matched and high quality caption for a given image. So, why is the similarity bucket strategy effective? It is because the similarity between the image and the text of the whole dataset satisfy normal distribution. Higher similarity indicates a strong correlation between the image and the text. Lower similarity indicates a low relevance between the image and the text, and it is possible a noise sample. In addition, each sample belongs to a specific bucket. Through model training, each sample is corresponding to a certain bucket. Therefore, during inference, by fixing the prompt to the best match, the model is forced to generate the highest similarity, best matched, and highest quality captions. The third strategy is retrieval augmentation, which provides a mini knowledge base for each image test pair during the training part. The model can not only extract visual features such as objects, attributions, and the relationships of the image, but also align the information of the image with the knowledge base. As shown in this figure, for example, in the question stage for each image query, we use clip retrieval library to retrieve top K image test pairs according to the similarity between image query and each image of the line file B. And then we extract the K captions from the top K retrieved image test pairs. These K captions are concatenated into a mini knowledge base and inserted into the template of the OFM model. Resulting in the template, what does the image describe? Retrieve knowledge, the caption is. Through this retrieved knowledge, the model can generate content-rich and diverse captions. The first part is the pre-training. We collect image test pairs from a specific URL on line file B instead of randomly collecting data. The pre-training objectives are conclusive learning and image caption. In addition, we employ the similarity bucket in pre-training part. The second part is clustering. We use clip retrieval library to retrieve similar image test pairs based on images. We apply simple data cleaning to filter out low quality data. The training objectives are also conclusive learning and imaging caption. Furthermore, we expand the template content by similarity bucket and retrieval augmentation strategies. The third part is fine-tuning. We further compress the training dataset from the clustering stage. We also incorporated the validation set of this computation into the training set. We also incorporated the validation set of the computation into the training set. Similar to previous part, we employ the similarity bucket and the retrieval augmentation strategy in this part. This is the model ensemble part. Specifically, we train in models to obtain in predictions and select one as the candidate answer and treat the rest as reference. Next, we calculate the sum of Cedar score between candidate answer and other reference. Finally, we select the candidate answer with the highest score as the final ensemble result. The training data at all stages are collected from line file B, a large-scale clip filtered image test dataset. Each image test pair in line file B includes an image, a text, an URL, and a similarity. In pre-training part, we collect 6 mini image test pairs based on specific URL, such as SumX.shutterstock.com, editorial.shutterstock.com, and all, and extract the top one mini image test pairs based on similarity. In costing part, we use all the computation images to retrieve external data from line file B through curl clip retrieval library. For each image query, we retrieve top 13 image test pairs based on the similarity between the image query and the line file B. Retain 120,000 image test pairs. In fine-tuning part, we also use all the computation images to retrieve external data from line file B through clip retrieval library. For each image query, we retrieve top 10 image test pairs with only URL www.tsctn.net, retain 12,000 image test pairs. In addition, we also add the 5,000 validation dataset to the fine-tuning part. In each model training part, the number of similarity buckets is 4. Noise, low quality, high quality, and the best match. In the cross-team and the fine-tuning parts, the number of retrieved relevant image test pairs are 1, 2, and 4, so that we can obtain different models to perform the model ensemble trick. In pre-training part, we load the pre-trained OFI large weight and pre-trained 5 epochs. The input image size is 318. The batch size is 16, and the input test length is 13. In costing part, we load the pre-trained weight from the pre-training part and costing 20 epochs. In fine-tuning part, we load the weight from the costing part and finding 100 epochs. From the table 1, pre-training, costing, and finding parts reach 170 theta score without retrieval augmentation and similarity bucket strategies. By using retrieval augmentation, the theta score for the model is 290. This strategy shows a remarkable improvement. By using similarity bucket, the theta score is 310. Finally, we reached the highest theta score by ensemble 20 models. Okay, this is our solution for this zero-shot image caption challenge. Thank you very much. Hello?
Someone
I forgot to turn on the mic.
try again.
Could you share your personal experience with the challenge? How you thought, how well, maybe how bad was the data or how good was the data, and what should we improve and stuff like that?
Is the mic on this time? We are not hearing you. Strange. Hello?
Hello?
Yeah, now we hear you. Yeah.
Could you say it again? I can't hear clearly.
The question is, can you share with
Mm.
us your experience during this challenge? Was it hard? Was it difficult? The data good enough? Anything about the challenge?
Okay. The difficulty of this challenge is the data set includes large variety of visual concepts for many domains and various image types. But we found the line file B dataset also includes large variety visual concepts. So we consider it use the line file B. The line file B denotes our external dataset, and
Very good, very good. Just last question, if you go to slide 7. So it was very interesting to see, go back to slide 7.
Yes.
Perfect, very good. So your OFA model was enriched with contrastive learning. So what was the intuition behind it? How did you think of adding contrastive learning?
OFR model is based on encoder-decoder architecture, does not contain contrastive learning. So we collect a large number of data sets and use contrastive learning per train objective and align new visual concepts. And we follow LBF and use the monitor model to generate the pixel targets.
Okay, thank you. I think we can thank our
Yeah.
speaker.
Thank you, Mr. Lee. I'm sorry. Next speaker is Youngtaek Oh. The title of talk is Retrieval-Based Data Discovery and Fusion for Zero-Shot Image Caption. Please welcome.
Oh, sorry, can I start? Yeah. Good morning, everyone. My name is Youngtaek Oh, and I'm the team leader of the Retriever in the next challenge. Today, I'm going to present our solution, which is the second place position in this competition. Before I proceed, let me introduce our team members. Me and Jeon are the core team members. In addition, we got advice from other three professors. First, we highlight some interesting properties we observed in the NICE dataset compared to COCO captions. First, captions often include descriptions of camera angle. And second, some images may be captioned with proper nouns like city or country names. We thought that these are the main challenge to improve the captioning performance in the NICE data. So we tested one of the state-of-the-art captioning model, BLIP2, on the NICE dataset and compared its predictions with the ground truth captions. Although BLIP2 performed reasonably well in quality, but it struggled to capture the specific knowledge present in the NICE ground truth captions. This highlights the limitations of relying solely on pre-trained or fine-tuned models trained on large datasets. Therefore, we mainly focus on incorporating this specific knowledge into our captioning predictions. With these observations, we present our solution, which consists of a captioning model and an explicit retrieval module to address the zero-shot captioning. Our approach aims to expand the knowledge of existing captioning models by retrieving samples from an external memory. This includes two separate stages. First, dataset discovery, and the second, retrieval-based fusion. Before explaining the two stages, we briefly discuss the components we've chosen for our framework. Our framework allows an captioning model that includes a vision encoder and a language decoder. And for our baseline captioning model, we selected BLIP2. In BLIP2, the intermediate transformer layers named QFormer connect visual and texture modalities. And our explicit retrieval module performs a k-nearest neighbor search on an external memory, retrieving the top k most similar images and their corresponding captions based on a given query image. We source the memory dataset from a subset of short data available online, and this counts for 1.1 billion samples. This retrieval mechanism enables to efficiently use a collection of diverse image-to-text pairs, which can provide contextually rich information in data discovery and fusion phase in the model component. We introduced the key components of our framework, and we then explain the two stages in our framework in detail. The first stage is the dataset discovery process, where we use the retrieval module to construct a training dataset first. Specifically, we treat the NICE dataset as the query and retrieve k image-to-text pairs per query image from the memory dataset. This retrieved dataset is then used for further fine-tuning with BLIP2. As we will show, the discovery of data samples that are highly relevant to the target task plays a crucial role in enhancing the performance of our solution. During the fine-tuning with the dataset explained in the previous slide, we go a step further and incorporate the knowledge associated with the input queries into our model by applying the retrieval module again. This approach allows the model to learn the knowledge that may not be readily available in the training data alone, such as long-tail learning and zero-shot learning scenarios. With this contextual information retrieved from memory, our model can produce more accurate and informative captions. In this stage, we utilize the QFormer to encode the corresponding captions of each of the top k retrieved images to generate the value features for fusion. To fuse this knowledge into our model, we aggregate the value features using the simple average operation and concatenate this with the original query feature. The resulting representation is then fed to the subsequent model components for further processing. For the fusion process, we explore two potential locations within BLIP2, the output level of the cubeformer and the input level of the cubeformer, or from the left and the right side respectively. We investigate these positions to determine the optimal point for fusion. And for experiment part, we compared different training data sets to assess their impact on the performance. The zero-shot approaches with only pre-trained BLIP2 or COCO fine-tuned BLIP2 produced unsatisfactory results. And fine-tuning on some randomly sampled shuttle-stroke image to text pairs also showed poor performance in terms of CIDR scores. On the other hand, training on the discovered data led to a significant improvement. And this shows the importance of careful selection and integration of the relevant data for training. And we tested the retriever-based fusion mechanism, focusing on different fusion locations. We evaluated two types of training datasets. One obtained from the dataset discovery process with a K value of 1 in the left, and a subset of the nice validation split with 4,000 samples from the right side. Evaluated on the remaining 1,000 validation samples, we observed that fusing on patch token embeddings, which is the input level of the cubeformer, showed better and stable performance with higher K-value. And to achieve the top performing entry, we combined our two approaches. Before that, we fine-tuned BLIP2 on 4,000 of nice validation data. And on top of it, we applied dataset discovery, and then those discovered samples are combined with the nice validation data for training. We then apply the retriever-based fusion on the visual patch token embeddings. For our final test model, we use the validation data for training and evaluated it on the test data. And this achieved the second place in terms of CIDR scores. And we present the captions generated by our model. In addition, from the right side, we show the top two retrieved images along with captions based on the core image. Through the retriever-based fusion process, our model can capture some specific knowledge and concepts present in the ground truth captions. And to summarize, we introduced some simple and intuitive solution designed to address the zero-shot captioning challenge. For a better understanding of our approach, we also share the code and technical report. So thank you for your attention.
Any questions?
Thank you for this talk. I think it was on slide 10 that you had the table, the initial table of results, where you compare performance on training on a subsample of the Shutterstock data versus training with this augmented data set that you create. So basically there you show that training on that subsample is inferior, and I just wonder, in theory, that the relevant images might not have been in the subsample, so that makes sense. What do you think would happen if you had the capacity to train on the entire Shutterstock data set?
Well, actually, the quality of the captions that we download from Shutterstock was we observed some noise. So this is the training without nice validation data, and when we only trained with some randomly sampled source of data, it showed some inferior results, and we thought that the quality itself, quality of the caption itself, was not enough to train our captioning model, because the captions are downloaded from web. So
So maybe one clarification here is when you say you train on randomly sampled data, do you still have this retrieval augmentation in the training on that data? Because at least what I understood from this was if you do standard fine tuning on captioned images, you don't get the same benefits that you do if you have this retrieval augmentation where you learn from the captions via retrieval instead of through fine tuning. But maybe I misunderstood the.
For this part, the table in the website, we did not use nice validation data for training, and it still can help. Sorry, in the randomly sampled data case, we didn't try the retrieval augmented approach yet.
Okay. Okay. Thank you.
We still have time for one more question. So if you have any questions, please feel free to ask. Or please give another round of applause to Youngtaek.
Thank you.
So our third speaker, Anna, unfortunately has the COVID. I hope you feel okay. And she cannot be with us today, but we are delighted to have her here talking to us anyway. So I think you're smiling, so I think you hear us.
Hi, yes.
Welcome.
It's really unfortunate. I was looking forward to being there in person, but just, yeah, I tested yesterday, tested positive. My kids might be sick though, so that I am gonna have a fun time.
Good luck with that. So I'll leave you the stage to introduce your talk.
Okay, just let me see how
Can you share?
Yeah, I will share the full screen in just a moment.
No problem.
All right, that should be the right one, hopefully.
Perfect.
And I will also just time myself in case. All right. Okay. Hi, everyone. Again, sorry I'm not there in person today. We'll do this virtually, hopefully next time. So I will talk about reliability and utility of image captioning, touch on some of the topics that I've been working on in the past several years, and some very recent work as well. So we've come a long way when it comes to both image and video captioning. I like to do this little show and tell thing that, you know, like when I started, things used to be templated, very like limited vocabulary, and now we have these open-ended captioning tools. You know, these features are part of many tools we use daily, and at the same time, there is always room for improvement. So a small thing I like to show is this PowerPoint demo where you can add an image and PowerPoint can suggest a caption automatically, like a giraffe standing next to a large rock, which looks perfect, like a nice caption, very Coco style. But in this case, it says it's a close-up of a mushroom, and well, that's not right. Or in this case, it says a picture containing outdoor groundwater bird, which is like super non-natural sounding caption, I would say. And finally, this example I like, it says it's a statue of a person on a pedestal in front of a building, which is by COCO standards, sort of very neat caption. But you could imagine that you might want to know more, that this is a thinking statue in particular in front of the Legion of Honor. So what you're missing here is some of the actual named entities, right? To give you much more information about what's happening here. And so to summarize, I think my work has been looking into these aspects of captioning that are truthfulness. So is it actually accurate with respect to the image or video? Naturalness. So is it fluent? Is it coherent? Would a human produce such a caption? And also usefulness or utility, because as we saw in the last example, sometimes you really want to have these named entities or additional capabilities to actually support a particular use case. And then how do we even measure that we're making progress? What are the right metrics for captioning? And so today I won't talk about the naturalness because this is a shorter talk, but I will talk about the other three aspects a little bit. So I'll start with the description usefulness. And in this case, I will cover our recent work on news captioning. Will be more of a spotlight in the interest of time. And so when I talk about use cases, what I mean is sometimes captioning needs to support a particular use case or scenario. So think about the example of captioning for the visually impaired users, such as the very famous VizViz challenge, right? We need to be able to handle unusual viewpoints, maybe some blurry images, read a lot of text and numbers from the objects that people want to know about, or movie description, where we need to understand the characters, understand the plot, or have some other additional sort of supporting capabilities. And finally, news captioning, which is this more recent problem, where you have to also understand named entities, people, events, locations, but also relate the caption to a larger context of an article. So let's dive into this recent work we just did jointly with Minyang, Grace, and Joe from Colombia. Just again, to recap, you're given an article. Oftentimes there is a title and a longer article, and then you have this image and you have to produce a caption. So this is not your typical image captioning, which is, a man with a tennis racket throwing a ball, right? This is much more complex. It's talking about Andy Murray, a specific individual at a particular event, and maybe gives some more additional global context as well, that he and Serena Williams will play together and she isn't actually on the photo. So how do we produce these kinds of captions? So some of the key observations we made from analyzing the data sets is that a lot of words that you need in these captions are already contained in the article. So this really might just boil down to retrieving the right information from the article. Yet, if you just use the entire article, it's way too long and there is way too much else. So it's really concentrated information that you need to extract, maybe a few sentences of the entire article, which are really relevant for that particular image. So we made like an Oracle experiment, and the details are in the paper, where we saw what if we just really found the best sentences from the article, and we saw that brings a huge improvement in captioning quality. So how do we get there? How do we actually get that sort of juicy, specific context that we need for this captioning? And sort of an overview here is several insights. There is, of course, the global context, such as the title of the article could be really important to convey what is this story about, or some initial few sentences, or a summary of the article. So the global context is important, yet it has to be restricted in lengths, because we don't want to handle like arbitrarily long articles. But what's more important is the local context. So what is actually in that particular photo that we are trying to caption here? So we're looking for visually grounded entities, such as in this case, Andy Murray, who is clearly pictured in the photo. And we're trying to extract that context from the article. So we are finding sentences which relate to our photo the most. But then some entities, like we said, may not be visual, may not be actually pictured. So for example, something like dates or locations may not be easily extractable from a photo. So we may also need to perform some additional relation extraction to say that something particularly happened on a Tuesday, right? Which is not something easy to do in just a kind of grounding fashion. So more formally, it's a very simple approach, and one could plug and play with different components here. We start with the article and an image. We use a vision and language model, such as a clip, for example, to extract several important sentences, which is how we capture these grounded entities. And then from there, we propagate information using a relation extraction tool to get to these non-grounded, non-visual entities. And then all of that forms that sort of concise, useful context. We select the sentences and then feed them into our news captioner, which is any model, basically, what we use, transform and tell, which produces then the captions. So just a few examples to kind of contrast what you get with using our approach, which is the selected context, the second row here, versus the original context from prior work, which is typically either the first few sentences and sometimes could be sentences around the photo. But we noticed that our approach provides a lot more sort of specifics and a lot more named entities propagate into the caption with this method. And another example here, as we see the original context sort of lacks some of the details of the story that may be important. And also the importance of the global context is still cannot be underestimated. So it's both. So this is some interesting nuances about this task of news image captioning, which I'm sure we're going to see more of in the coming years, as this task is quite relevant. And next, I would just very, very briefly recap some work we did a while ago on the metrics, because it's related to the following part of the talk. So very briefly, how do we score captions, right? What's a good caption? So there's many different axes to this. In this particular one, I want to talk about object hallucination. So we oftentimes produce captions which contain some hallucinated stuff, right? A woman talking on a cell phone while sitting on a bench. Well, there's no way of knowing if there is a bench, in fact, in that scene, but well, from our perspective, it's a hallucination. There is no bench in the photo. So how do we score such a caption? And the standard metrics don't accurately reflect or penalize this kind of hallucination. So what we did in 2018 work, we proposed these metrics on capturing this hallucination at the sentence level or instance level, which are very simple. You're just sort of trying to score your captions against the ground truths, considering that you know the ground truth objects in the scene. So this requires some additional annotation, which we do have in MS COCO, but maybe not in all the other data sets. And then we see that with this metric, where sort of, in this case, hallucination, the higher, the worse it is, this can capture and accurately reflect this phenomenon. And one could potentially combine this with other metrics. But just going back to the main sort of presentation for today, this around description truthfulness or correctness of captions to images or video. So to tie it all together, I want to talk about this new work about token level confidence and how this could help improve caption correctness and also reduce hallucination. So basically, we oftentimes rely on these large-scale vision language models to score images versus captions, and maybe that can tell us, okay, there is a score we can produce for this pair of an image and the caption. But recent work has shown that if you just kind of mix up the words in the sentence a little bit, you might get unreliable measurements. You might actually score the wrong caption higher than the right one. So this diagnostic data set called Winterground challenge basically, does some permutations and other sort of compositional probes to see how well models are doing. And they basically find that there's many issues with how the large scale models handle this. So they lack, they don't accurately capture these fine grained details. Now, on the other hand, yeah, I guess this is just to sum up. So this coarse sequence level supervision seems to maybe lack to reflect some of the fine grained details. On the other side, when we do image captioning, we do supervise at the token level. So we always gonna score every little bit of information, right, as we produce a caption. So we thought, how could we sort of bring these two things together? So we took a pre-trained large-scale model, fine-tuned for captioning, and now when we feed in an image in the caption, and the caption could be from this model or a given caption from someplace else, we want to produce these token level confidences and use those to then maybe aggregate and have a single score for convenience, which could then guide us towards, is this a good caption or not for this image? So more specifically, this idea, which we introduced, this token level confidence, TLC, could have two different ways of implementing it. The algebraic one, which is very simple, no learning involved, or the learned version. So let's talk about the first case, and I'm just going to very briefly show some results, and the rest is in the paper. So here we choose softmax as a very simple way of looking at the confidence at the token level. And we go to this Winogrand diagnostic benchmark again. So look at, on the left, you see two photos and two captions. And so the task is to basically accurately match, each caption to each photo. So there is a bluebird, red berry, and a redbird, blueberry. And so we see how we are doing. We use OFA, a recent, quite powerful model, which does really well in captioning. And we see how it struggles initially on this task, and introducing our TLC with softmax gives us a big boost and even outperforms the previous best result on this benchmark. So it's really powerful and very kind of a simple approach, shows quite clearly its advantage here. So if you, however, have some data that you can train on, some additional annotated set, you could actually do even better by learning these confidences or training a dedicated confidence estimator for your particular model. So let's see how that works. In this case, we have a frozen captioning model, and we're going to learn this additional model, a correctness estimator for that captioning model. So it's going to look at the predictions the model is making and take some intermediate features from the model. And it's going to be trained on a binary task. Basically, will the model get this right or wrong? And so if you do this, so here is an illustration how this happens sort of as we look at the caption. So here is a ground truth caption, a dog sleeping next to a big teddy bear. And so say our model at the step 3 is predicting standing. And we want to basically score, we want to estimate the correctness of this token. So using our correctness estimator, it will look at that word, at that token, and basically be scoring it against the ground truth, which is sleeping in this case. So it's going to be penalized, and that particular sentence overall is going to be penalized for this sort of hallucination. We also found that using a postfix, so not just the previous words, but also the following words from the ground truth can help us get even better estimates, because this context is really useful. So how this works in practice, it's very simple. You're just going to go over your beams. And so this is, in this case, restricted to just COCO words. So we're going to be rejecting those where the confidence is lower than a particular threshold, which we could set on a validation set. And we will do this until we find the beam which satisfies the threshold. So we find the caption which is free of hallucination in this case, because there is no person anywhere in the photo. We found that this overall helps reduce hallucination. So these are our metrics that we talked about previously, the chair metrics. So we improve on those. We also improve diversity of the captions. And there is a small sort of price to pay in the standard metrics, but I would say this is kind of not super clear if this drop is actually significant and whether we should be concerned. But I guess maybe more analysis could be done there and more human evaluation as well. Right, so just some examples. You know, the model can kind of reflect that apples may not actually be present in the picture. It's hard to tell, so it backs off and predicts fruit instead. Or scissors are incorrect for this photo and it's corrected to a knife. Again, something with apples. Apples are not in the photo. It's a hallucination, so it's corrected. It's removed out of the caption. And in this case, a metal chair. Chair is a very popular noun in Coco. It oftentimes gets output with high sort of frequency. So we remove that here because fence is actually more accurate. So there you go. It's a sort of a short presentation, a kind of a run through some of the ideas around description usefulness and the emerging tasks, which I am very excited about, like news captioning, the recap on the metrics, and a longer sort of dive into this recent work on description truthfulness, where we have this very simple and quite effective method to measure image caption correctness, which we show reduces hallucination by quite a bit. Those are the papers that I talked about. And with that, I think I will conclude. Thanks for your attention. And a very short moment of advertisement. I wanted to share that I will be joining at TU Darmstadt in September as a professor. So looking for students and happy to get in touch. If you're interested, let me know. Thanks.
Well done. Congratulations to you, Anna.
Thank you.
We are delighted to have you in Europe in an amazing university, and definitely many students will apply to your call.
Thank you.
Amazing presentation. I do have a question for you, but let me open to the audience here first. Any question? Yeah, sure. Yeah, the mic there. And in case you don't hear properly, let me know and I will repeat the question. Can you say your name and your affiliation?
Sure, I'm Sam. I'm from the DoD. I had a question about your news image captioner. I know that was just kind of the preamble, but you showed how it could do that news style caption where they kind of repeat their context or their topic, even if it wasn't relevant to the picture. And then you showed how the highlighted text provided that context, right? Was that human selected context, or did the text model identify that as the context to then use for the caption?
So in the examples that I showed in the last slide, that was all automatic. So this is what the model has identified as relevant context based on the image and analyzing sort of some of the global context and sort of both the global and the local context, the local being the photo. This has not gone through any human eval to say, would the human agree or disagree that this is important and so on.
Sure, very cool, thank you.
Yeah.
Great question too. A follow-up from me, Anna, if I may. Same part of the presentation, talking about name entity. I love that part. However, coming from Shutterstock side, we know editor by images from our library and then attached to specific article. Sometimes those images were taken a year before. It was maybe another match where that specific player was playing and things are reasonably similar to be used. Sometimes it's really in the moment. We have Shutterstock photographer at the red carpet in few seconds, uploading the picture as they take. So for the newspaper around the world to use the latest, the moment.
Mhm.
So there is a difference in the editorial world on picking an image for a specific article and picking that authentic image in the moment of the event that they are describing.
Yeah.
Within your model, it felt to me that there is no way to discriminate in which of the two situations we are when we
Mhm.
create a caption, unless we use some information metadata that is attached from the
Mhm,
content itself. So I wonder if you guys have thought about that problem.
I think what would be really more comprehensive is to see the article as a whole and consider that maybe there's multiple photos in the article, right? Maybe one of them is just showing somebody's headshot and that's very boring and it's just like blah, 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 this person. But then the other one is much more, like you said, specific or like event centric, where you see a particular thing and you could say, oh, this actually happened. And this is the event I'm going to talk about. So I definitely agree that there are these different flavors of imagery that we see in the news media, and some of them are this more generic, and then others are more specific. We think about this a lot in the context of also forensics, when we are like trying to see if something is true or false, because these generic photos, you could like snap them with any caption and it works, right? And for others, you need a very, very specific one. So I feel that if you analyze an image and you can extract information out of it, the more details the image contains, potentially the more matches you will get with the article and the more entities you may be able to spot there, versus these more boring ones, maybe you only can get one name and little else. So I feel like implicitly this may be captured, but I'm sure that one could do much more in getting the overall kind of story and the overall context more explicitly captured as well. Yeah.
Very good, very good. Thank you very much. Your talk was really good.
Thank
Any other
you.
question? No? So sorry you're not here. Hopefully we'll meet in person very soon. And good recovery to you and to
Thank
your
you so much.
family.
Thanks
Bye,
for inviting
Anna.
me.
Thank you for being with us.
Bye.
So our next talk is from Jack Hassel. No? Oh, sorry. Oh, we swapped. Okay. So I'll give you. Introduce yourself. So a warm welcome to Cordelia Smith and talking about the large-scale learning of multimodal video representation. Thank you.
Yes, thank you for the introduction. So my name is Cordelia Schmidt. I'm a researcher at INRAD at Google part-time. Today I'll actually talk about two recent works on captioning. So basically we all know to access the large amount of data which is available online, we need to have some textual information describing them, which can be obtained by captioning. And so what's important is we need to have multimodal representation. So if you look here, we can see a man serving food to a woman, and only if we hear the question, is this food Indian? Do we know what kind of food the man is serving? First thing, and then second thing, there's a lot of data available on the web. So for example, here you can see the data set How to 1 Million, which comes with video clips and ASR transcribe, which describes more or less the content of the video. And this allows us to pre-train or train multimodal video representations. And so today I'll present two recent works. One is on dense video captioning, so how to caption long videos. And the second one is how to augment visual question answering and image captioning with retrieval. So first, what is dense video captioning? Most of the recent works actually just take video clips, which are already segmented and produce captions. Here, what we want to do is to go one step further. We have a long video, movie of an hour, and we want to caption the different events in the video. These captions should be grounded in the video, so to say where exactly these captions are in the video. And what we can see here for the example, it's not disjoint, but the captions, they can actually overlap. So for example, we can have one event and the second one is occurring in parallel or slightly shifted. As you see here, an elderly man is playing the piano in front of the crowd. A woman walks to the piano and briefly talks to the elderly man. So what we really have to do here is to combine localization to say where these captions appear and text generation. And ideally, we would want to do this end to end in one go. And so what do the current state-of-the-art approaches do? What they have is they have actually often separate networks for localization and captioning. This is not ideally, because ideally you want to really do these two things jointly, because depending on what caption you produce, the localization can slightly change. And then in many cases, they're just annotated in very small data sets. And it's also not ideal because you want to have access to large amount of data to pre-train these models. And then in parallel, so this is something we're building on, is peaks to seek, where you can actually see what people have done is they cast object detection as sequence generation. So what they do, they localize the objects, they feed in an image, peaks to seek determines jointly the localization of the object and the category. So this model spatial coordinates are quantized and tokenized. So you can really produce as an output the coordinates and the text description end to end. And so what we do here, we push this one step further, and we want to produce a single sequence of text and time tokens, which combines localization out captioning. So we have a long sequence as input here on the bottom, and as output, we have like the time steps with the time tokens and the captioning outputted jointly. This is the task on our model. And then what's important is the pre-training. Given this is a large-scale model, we have to train it, and the downstream data sets are very small. We have to train it on large-scale narrated videos. We have the video content, and we can use the ASR to A, chunk the video into clips, and B, use the ASR as captions. So here, an overview of our model. We have a frozen backbone, which is based on pre-trained clip features, a text-trained encoder, but then given that our description is multimodal, we also have the ASR as input, right? So with the vision as input and the ASR as input. And for the ASR, we have in addition to the transcribed ASR, but in addition, we have the time tokens also encoded. So what we do is we have the boundaries of a given sentence, and then these boundaries are whatever seconds, and these seconds are quantized into an interval. So we say basically everything is the time step, it's 100, and so we kind of say where in this relative time steps this ASR appears. Okay, this is the input. We use a T5 encoder decoder, and then this is fed into the decoder, and the output, what it produces, again, produces the time tokens. So here, for example, 1 and 17. So this is discrete time tokens, the corresponding caption, the next time token, and the corresponding caption. So it outputs this full sequence. And for pre-training, we use 15 million YouTube narrated videos from YT Temple 1B. So these come with ASR. The ASR gives us the sentence boundaries, and which are used as event boundaries, and it gives us a proxy textual description. So what we do now, we can pre-train using this ASR as output. So we output the time tokens, which is the boundaries of the ASR and the ASR. And then that's the first loss. And the second loss, given that we want to also pre-train for multimodal inputs, we also mask out parts of the speech and then predict the masked out tokens. This is our denoising loss. So we have these two losses. This allows us to pre-train jointly on the two modalities. And then if you compare the state of the art, so here are different benchmarks. On the left, we have dense video captioning. So here we have UCOOP2, VITT, activity net captions. We can see that especially for UCOOP2 and VITT, our model significantly outperforms the state of the art. Then similarly, we have video captioning, paragraph captioning. So you have a video as input and we produce a paragraph caption. Again, we can see that our method outperforms the state of the art. And then even if we use it for video clip captioning, we still outperform the state of the art. And then I won't go into details of the ablation studies, but if you look at the paper, what you can see that is pre-training is, as always, very important. Of course, the data set and the quality matters. So basically, the better the quality of the pre-training data set, the better is the pre-training, right? So we've been recently doing some additional studies where we use chapters for pre-training that further improves the performance. Then the time tokens help when pre-training on untrimmed videos. They allow to predict the localization. And then also what's nice is visual and speech information are really complementary. So for some videos, actually for YouTube, the ASR is really relevant. And so only using the speech, you can already get very good captions. And so both, basically using both together, it's really important. And then also the importance of the loss, the denoising loss is important if you use speech during pre-training. So again, it's very important to have the right losses for training. And then some quality of results, what you can see here, the frames, the input speech. So I don't know if you can read it, but you can see actually the input speech gives you already a very good idea what's going on. Then you can see the ground truth, and then what our Vis2Seg model outputs. What you can see, it finds the boundaries quite accurately. And if you look at the produced text, you can see that it's also very good, but it's not always exactly the ground truth, right? So this is what also Anna mentioned, that basically the evaluation of this captioning metrics is really difficult. So sometimes actually what our model produces is better. If you look at it, it's better than the ground truth, but obviously the score won't improve. But anyway, you can see that it gives nice results. And then similarly for sports videos, you can really see it gives, if you look at the videos, you can really see, I don't have the videos here, but you can really see that the captions we're obtaining are really satisfactory. So for example, here, a woman runs with a javelin, she throws it into the field, she throws the second javelin, she waves to the crowd and folds up a flag. So you can really see the description is very good. So in conclusion, we have seen that we obtain excellent results for dense video captioning. Problems which are remaining are the metrics, the variation of the annotation details, and training for specific domains. So basically these things are still things which currently work on progress. And then open object issues are small objects are not detected, rare events, hallucination, answers, and explainability. So again, it's very similar to what Anna was talking about. And I'll just give an outlook on work, what we're planning to do for the small objects. So if you want to also take into account objects or small objects, it's important not only to look at the full image content, but also to caption the objects in the video. And this is current ongoing work, which is dense video object captioning, where we don't only caption the sequence, but we get the objects extracted, the tracks of objects, and then we produce caption for those. And this way, we hope that we can get even more precise captions, right? And of course, one of the things which are the problems you have is also the training data, because basically given the training data, the details vary a bit. But this is really the next step, I think, for me to kind of go one step further and get these captions. And then the second part of my talk is basically retrieval augmented vision question answering, and then also image captioning. So what's the idea here? If you have these large language models, basically we don't really know what's in them. They produce an answer, but we don't really know what's going on. And also we don't have any very fine-grained information. So for example, here, what is the American president associated with the stuffed animal seen here? Basically, we need to have very fine-grained information to be able to answer Teddy Roosevelt. And so basically here, the idea is that in addition to these large language models, we also have a knowledge base where we store wiki image text, wiki data, and so forth. So we can store additional information, retrieve this information, and then feed it into this large language model. And more detailed the questions are, the more important it is. And so why, in general, why do you want to go towards this memory knowledge? Actually, basically, these large language models are dedicated to high-level reasoning, and often this is not fine-grained enough, and we don't really know what's going on. So what we really want to do here is to disentangle knowledge from reasoning and to be able to use existing knowledge. And furthermore, this retrieved memory knowledge can be used to interpret the model and the decisions. And then something we're also looking into is how to use it for incremental learning. Okay, and then here, illustration. So vision question answering is nice for an illustration because there basically you can ask really tricky questions, which part of this meal has most carbohydrates. So you really know to first recognize what are the different staples in the image, and then how much carbohydrates it contains, right? And then you can give the answer rice. And so here we saw before, basically, we have one of the problems we have is no supervision for which retrieved items are relevant. The Q&A pairs we have are small. And so what we do again, we pre-sort again to pre-training. So what we do here is we have a pre-training corpus, which are images and captions. We mask out parts and then use our large scale memory, retrieve the corresponding items, and then output the answer. And then you can back propagate through this whole system. And this allows us actually to optimize the parameters of the system. So basically to pre-train the whole system and then fine tune it. And this gives us an idea which items are actually relevant and how to set up the whole retrieval and so forth mechanisms. And then what's the system? Basically, we have a model encoder, which takes the input, the question, and the image. It's a T5 base encoder, gives an output feature vector, which you then project to a query. This query is actually used to match the keys in the memory. So the memory we have for each document, we have values for which we produce keys. These keys are used to match the query to the keys, to the documents in the memory. We also have a mechanism which is corpus gating, so we can actually decide in which corpus to search. And then this gives us a weight, and this allows us to weight the different memory items retrieved. Basically what we get here is we retrieve a set of memory items with weights, and these then added to the decoder, basically. So knowledge intensive fusion matrix, attentive fusion, where we have the weights and we fuse this information to the query. And then we have a decoder, and that gives us the output, right? So basically you can now basically combine the predictions from the encoder with the query, retrieve the memory retrieved, given them the query, and then use this whole information, feed it to the decoder. And then here the results on OK VQA. So this is one of the outside knowledge VQA data sets. So basically there it was kind of constructed to have the necessity to have outside knowledge. So it's a bit different from general VQA. There are other data sets which are even more extreme. So basically here, if you compare to the state of the art, the top rows show results only using the memory and some transformer. Then the next part shows using memory plus GPT-3, so a very large scale model. So you have a very large number of parameters. And then our approach actually has much less parameters and outperforms the previous approaches. And so what's also nice is it works better. We're currently working on other data sets. Obviously, it's data sets dependent. So if the data set needs more outside knowledge, the performance improves. And you can see here 2 examples. So the input is what flag is on this umbrella. The top 2 retrieved knowledge. You can see basically it's 2 items about the English flag, and then basically ground truth is England Union Jack, and our prediction is Union Jack. And then similarly, where in the world are these grown? So basically it recognizes that it's Saba bananas, and then it says Philippines as answer. So again, what's nice here is you can really see what is actually used for your reasoning. So I think this is A, the results are better, but then B, also you know what is used, and you can actually show to the user what has been used to answer your query. And I don't know if I have still time. And then basically here we have some experiments to see how important the knowledge is, and you can see the more knowledge you remove, the worse the performance is. So basically you can really see, so here what it shows in the bottom is no retrieval, top, all sources, and then if you remove the sources, you can see that really the performance drops. And what's also nice is the orange curve is during training and fine-tuning, the knowledge is removed, but then it's added back again during inference, and you can actually see that if you have a small amount of data to train the model and add it back in, it still gives a much better performance than if you don't add it back in. So it's quite flexible. And then here again, you can see that different knowledge sources help. So basically the most important here in blue, only one left. So if you only use one, the VIT gives the best performance, but they're kind of all contributing to the performance of the overall model. And then given that this workshop was an image captioning, we also showed that it can improve the performance for image captioning. So the improvement is maybe less significant, but again, image captioning, you don't really know what the metrics are. So for example, here it would be a good way of getting the actor, right? So if you have the actor, you find the actor, you can really inject it and get a much better performance and see actually what's going on. Okay, so we have seen that we get excellent performance with large scale models with this retrieval augmentation. And we have also seen that the quality of the retrieved items is very important. And then one outlook, so this is just the first step. And what we're currently looking at is to further use these LLMs for reasoning. So here we have just added the knowledge, but now we want to also evaluate with the LLM how important the knowledge is, and then go one step further and say, for example, this image which you have just retrieved is not important. So this is the selected objects, then reject it, and then go one step further. This is actually current work, which is on arXiv, and we can show that that improves the performance even further. Okay, thank you for your attention.
Amazing talk. Thank you very much. Question? Maybe while you think about question, so much information has been shared, how you cannot have a question here. So I'd like to start maybe. In the first part of your talk, you were talking about segmentation first, and then captioning on the different segment. Did you do the segmentation a priori, or are you assuming that that segmentation is already done?
So the segmentation for pre-training, it's done based on the ASR, but then once the model is trained, it outputs the time steps, the tokens, and the captions in one sequence, right? So we have a long video and it just outputs the time steps, which are the segments and the captions. So it's all automatic and all in one go, right? So this is kind of the novelty of the method, that it doesn't need to do the segmentation first and then the
Amazing.
captioning, so it does everything jointly together.
So cool, so cool. Question? Yes.
Yeah, thank you for the nice talk. I was a bit curious about for the first part as well, when you were talking about incorporating the ASR information. So I noticed that there's actually a lot of knowledge in the ASR, like in terms of like proper nouns and like the actual people, but the caption itself is still more generic. Curious about your thoughts of like what would be the optimal like level of detail or hierarchy of information in the caption to be useful.
Yeah, so you're asking, so basically we have evaluations with and without the ASR, right? So you can do, I mean, in the paper you have video, ASR, and both combined, right? So this is all there. And I think the level of detail of the captions is like one of the things, this metric question, which is coming over and over again, right? And I don't have a good answer for this. And I mean, like it was also Anna's talk, right? I mean,
Yeah.
people are working on it, but it really depends on what level of detail you want, right? So basically, I mean, ideally you want all the details, right? But the caption metric, I mean, that's also when I showed the examples. Sometimes what we get is actually better than the ground truth. I mean,
right.
So, but then what can you do? Basically, okay, you can annotate more, but then maybe you have a level of detail which the user doesn't want. So I don't really have a good answer for this metric question, right? So I think this is something I'm kind of interested in, but given that it's user specific and the details, maybe you're interested in knowing that this is a person, whatever, X, and somebody else is not interested in it. So,
right.
And so I'm not sure. I don't have a clear answer what is a good metric, but I think it's something to give some thoughts about it. And that's also, when I went to this object-centric representation, I think this gives you like maybe some idea that you have like these objects, then you combine them and you can have different levels of granularity on how you combine the objects. I think all these captioning metrics, I mean, I don't know if you've worked on it, it's just combining strings basically. So it's not satisfactory at all, right? So it's kind of a proxy and it might not even be meaningful in the end of the day.
I can see maybe at the end, like depending on the use case, give different levels. Like for example, you could even figure out the theme, like what is the event? Is it Christmas? And then going to like a woman is something, and then to the actual woman's name. I guess it's
exactly.
Hard to
It's
say,
really depending what the user wants. And then obviously one solution could be that you get all the details, right? A woman, you give the name, the woman, blah, 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 is doing this, blah, 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 blah. So you have all the details and then you can extract it down maybe with some language model. You could say, now I want to reduce this information. I only want to keep the information about the clothing or the background. But So I guess with this object thing, maybe you could have all the details and then abstract
Right.
it down. I mean, we
Yeah.
tried this for now, it didn't really work. So because the objects are still a bit noisy, right? But once you have them well localized, I think then you could really say, now, this is what I'm interested in, and then I want to abstract it down. And then the evaluation is another problem, right? How do you evaluate
Right.
it? I guess then you would have the prompts plus for each prompt, the evaluation. Maybe possible, right? And then you
Right.
could have a user maybe annotate the different things which you're interested in, but.
True. Thank you so much.
Any other question?
Actually, it could be some basic question, but I want to know how Fusion actually worked. How you actually perform Fusion?
So, sorry, how?
Fuse the data, Fusion?
In
Yeah,
the
yeah,
in
Fusion
the
style.
in the memory retrieval.
Yeah.
So basically what you have is you have the query which comes here, and then the k retrieved items which you feed in one after the other into the decoder, right? So you have X items, like 10 items which are retrieved, the best 10, and then you feed them in. You have some waiting, and then you feed them into the decoder all jointly.
Okay, thank you.
Very good. There is one more question, just one more, very fast. How can you say no?
Thank you. I really like the talk. About the second talk, you explain how it works for VKI. And I was wondering what is the difference for image captioning, because now we no longer have the question, we just have the image. Now that works to retrieve the documents from Wikipedia and so on, because for instance, for Coco, sometimes the images are so general that I wouldn't see retrieved documents that could actually be beneficial for captioning. So I was wondering.
Yeah, so basically the query would, in this case, be just a visual query and then retrieving on the visual query, right? But I agree, it's maybe less, also the gain is less significant, right? So I think for vision question answering, if the questions are difficult, it's more beneficial for now. But basically what we are now looking at is to go away from the image content. That was the second part of the objects again, right? So then you could have a face, get the name of the face and incorporate this, and then you could get further improvement, right? Right now it's more, it gives a small improvement because basically, I guess, I don't know, I haven't really looked at the results, but what intuitively you get some additional information, right? So maybe if something is not exactly precise, you get some additional information to do the captioning. So yeah, instead of having just one image, you have 3 similar images, and that always helps, right? So I think that's why it would help, but I think in the future, it would be more to go for additional information, right? This is what I showed in the second part, the last slide that you get for object-centric information, and then maybe remove it or add it, right? And
okay.
In this case, you could imagine that even for image captioning, it could help, right? Not
Nice.
just the vision capturing. Okay,
Thanks
thank
a
you.
lot.
Another round of applause. Thank you very much. Thank you. So our third speaker is Hamid Palangi. Hamid is a principal researcher at Microsoft Research and affiliate associate professor at University of Washington. Welcome, Hamid.
Everyone, good morning. Thank you so much for attending today. And thanks for the organizers for inviting me. I'm very happy to be here. So the title of my talk is Lost in Translation, is also the name of the movie from 2003. And I hope through my presentation, I can raise more questions than answers for you. So I hope you leave my talk with a number of good questions. This is some of the materials are from myself and also my colleagues recently. So first, I want to convince you that image captioning evaluation is difficult. I think you have been already convinced because we have this workshop here, but I try to reinforce that more. And then discussing a few possible ways forward. And if time permits, I will also talk about relevant work for text-to-image generation. What do you see in this image? So this is a COCO style caption generated by ALT text feature Adamus PowerPoint. A group of men standing in a room. Is that interesting for you? If, let's say, if there is it is informative because it is COCO style, is great, but does that engage you if the utility is engaging the users? For this one, and a group of people standing in a room. So there is improvement because, you know, now there are women as well in this thing, so there is that recognition, but still there is nothing there about these two people looking at each other. And that's actually the state of things as we talk. So let's take a look at one of the great models, OFA, which is on the top of the leaderboard of COCO. And let's try these images with OFA, and thanks to them to make it publicly available. As you see, still we see COCO style captions, which I read because it's with a small font. A group of men in a room posing for a picture, a group of people standing in the room. So there are three important sources of difficulty that we are talking about. One is matrix. How helpful are the evaluation metrics that we try for the usage goals? And this is relevant to the first talk today about the utility, which is very important. The second one is data. How representative is the data that we train our models and architectures for? Do they represent the real world or target or motivation that we make for applications? And actually, I want to push a little bit more on this. We hear a lot of motivations for image captioning is around, you know, helping with the blind or visually impaired people. And also other applications like indexing search results, describing images using virtual assistants, helping non-expert to interpret domain-specific images like X-rays. But the most commonly used motivation application is helping the blind or low vision users. But previous work has shown that the data sets like COCO or conceptual captions that we use often do not meet the stated needs for them. And of course, we have other data sets, but basically when we collect these large scale data sets, they're not usually specifically targeted for the specific utility. And the third one are the models. How much of the issue is coming from different components of the model? Because now we are talking about the complex applications where the errors can propagate from the object detector, image tagger, or language model all around, and how to disentangle them. And also, can the loss functions that we use or architectures gain the matrix? For instance, when we optimize for side, are we gaining the matrix or are we actually improving the utility? So the common matrix, as most of you are familiar with, are the matrix from the text generation community, like Blue, Rouge, Meteor, Cider, which are doing the evaluation based on engrams, which is great to find the lexical similarities. Another one is a SPICE, which uses the scene graph of the image and a dependency parser on the captions, which also includes more information than those previously mentioned metrics, and a group of other metrics like purchase score or similar model-based metrics that try to capture semantic similarities between the reference captions filed in the case of COCO and generated caption, along with other proposed metrics in the literature. There are a number of questions to think about, and I just list them here and go through them. First of all, context understanding and common sense in generated captions is complex and quite challenging to measure. Actually, we have a number of wonderful data sets, and it is actually an important question to think about. For instance, in the example that I showed you, what is the context of those people standing there that we can understand what the models can? Noting that the evaluation is subjective, given the creativity of the task. The coverage is quite important. For instance, if we collect one image description from the web or 5 reference captions in COCO from human annotators, would that cover all the aspects of the image that we wanted to? Measuring the visual grounding is challenging, especially when we want to think about aspects beyond the object name grounding, between the object names and the bounding boxes in the image. And when we do object or attribute or relationship detection, there are ground truth labels. We have visual genome, we have open images and other data sets. But for image caption, there's no gold label. And text generation in general, which makes it actually much more challenging how to think about that. It's actually quite hard to interpret the captions. Out of all the objects, attributes, and relationships detected by a given detector, why the language model decided to select some as salient and generate, and to ignore the others. User studies are essential, but they are time-consuming. Even humans have biases. How to address this? Evaluation metrics should cover different aspects, different languages, and different aspects of them. There are progress there, but how far are we there? Are we making things too good for English? We need matrix that account for various deployment constraints. For instance, when we have this cool idea and we show, improvements on the academic benchmarks, why don't we also take into account the important constraints for shipment and deployment? Because if you really want to use them in a larger scale setting, those are also important. Why we are not reporting them? Do we hope that in future it will be solved, or it's not a quite important problem? Because it is if you want to deploy things. How do we measure the factuality versus creativity? For instance, in the case of hallucination that was discussed today, if you make things too factual, then they are boring, or if you make things too creative, then they are not factual. How to evaluate long tail and out of distribution? No caps is great effort toward that, but what else we have done there? How to evaluate for real world perturbations? It's quite common practice that we compress and decompress videos and images, and actually we are presenting a paper at CVPR this year around these real world perturbations, how they impact the performance of these models. Not just adding noise, but actually the real perturbations. And how to incorporate the user feedback in the matrix and evaluation process. Do we look at the evaluation process as a continuous thing to do, or we look at it as a static step? And do current metrics account for the interactiveness and dialogue scenarios? Is it trivial to extend them to measure the quality for the conversations? There were efforts from a few years back, like visual dialogue and such, but how representative they are and also the data sets. And finally, how much we think about creating metrics to measure the fairness related harms. For instance, the generated captions, they are picking up the most salient aspects of the image, which by nature is subjective, meaning that the system might show differential treatment toward various social groups. The generated attributes and verbs for specific objects might be systematically assigned to specific social groups, but not others. And the issues in above two items might be caused by object detector, tagger, or language model, or a combination of them. How do we know what is what and which is which? And with the language model, has a tendency to erase objects and tags related to specific groups of people. Do we measure for that? Do we account for that? So these are important. Now a few possible ways forward. We can pick one and just enforce it explicitly. For instance, in the case of relations, this is a work that we did a few years back, that you care about to create the important relationships. You can enforce it explicitly, starting from the data again. So this is what I'm showing is a screenshot on the right from a neuromotics paper, on the left from a visual genome paper. On the left, that's how visual genome is created, the number of boxes and description of those. And the right, it shows the statistics of the relationships in the data set. And as you see, most of the relationships, more than 90% are just geometric, which is quite easy to predict. Actually, there has been work to create a visual-free, simple feed-forward neural net that tries to predict the obvious relationships in the visual genome, where you give the embeddings of the object and subjects and predict those. And it can do a very good job at predicting those relationships, but then in turn, we can use it to filter out those relationships and only focus on the semantically challenging relationships from visual genome, which in this process, you end up with from 500 relationships to 117 relationships. And then trying to train your single generator or object detector and relationship detector on those relationships. Because there, the value is not to perform well on the top 50 relationships in visual genome, but actually to work well in a downstream task, which is image captioning in this case. And as you see, from this work, the relationships that are created on the bottom from these processes are actually more semantically challenged and diverse. And again, take this example that you generate a bunch of object embeddings and relation embeddings between those objects. And then if you train on these semantically challenging relationships, and basically this is a work that we did a few years back where we tried to explicitly enforce the attention mechanism to follow relationships separately from the objects, basically features of relationships and objects, and gating mechanism there. To improve things for both information, text image retrieval and image captioning. And, we showed that it can improve things, as you see in these examples, where the baseline models focus on obvious relationships, or model actually focuses on more, semantically meaningful and interesting relationships. I don't go through them. Another way is to, when we do the pre-training, we actually make things beyond image captioning. Basically, when we do this pre-training for the large models, we make it unified in the sense that it covers image captioning loss, but also it has a question answering component where basically you challenge the model during training about the aspects that are not covered in conceptual captions or COCO. And here we did a pre-training phase, having that in mind, having both accounting for both image captioning and visual question answering, and trying to improve things on both sides, especially for image captioning, because you can become quite creative when you create questions to improve things for the caption. Another aspect of this is actually, collecting data sets that are more interesting than COCO. COCO is great for research purposes, but if you take a look at this distribution, on the right, you see the distribution of the top 40 words in COCO, most frequent words. And on the left, you see we actually released a data set called NICE a few years back, which is a good coincidence with this workshop. But there we focus on more of generating more interesting captions, which cover more human, aspects of things. And it's about 2 million images. But there again, it's a lot of effort collecting this data, annotating them, and making sure they're covering these different aspects. But that's not perfect either. But that's another important step forward. Another thing is to think about evaluation as a continuous process. So this is a new work by my colleagues at Microsoft Research, Ada Vision, that basically they create this adaptive loop between in a given captioning system or object detector system, where they open the user feedbacks with LLMs like GPT-3 to create more failure cases, and then using those failure cases to fine-tune the models. And also, this is another work from my colleagues at Microsoft Research Junior, where they have this process for measuring the representation harms, where basically they focus on stereotyping, which occurs when you have oversimplified beliefs about social groups, and demeaning, which occurs when social groups are cast as being lower status or less observing of respect. And we actually look into the image captioning scenario with the state-of-the-art models like NVL, and they show how to measure these aspects and actually account for them. Another thing is, looking into explainability methods, but not just visualizing the attention of the trained models, but black box models like SHAP. This is from my colleague Scott Longberg from Microsoft Research. Basically, given a caption, they have this, game theory utility between the decision of the model and the input image to identify the most important parts of the image. And none of the explainability methods are perfect, but having them in the evaluation loop might help to give some interesting insights. And I want to also mention this because this is actually has become quite important, with the advent of quite large language models like GPT-4, and now with open source models that are imitating GPT-4, like Llama, LVQNA, Orca, and other models. How to leverage them to actually enhance the experience in the image captioning? Because as we thought, there's no gold label for image captioning. If you fine-tune things too much for COCO, you are going to lose a big opportunity. And this book is actually quite new, where basically you can upload the image and have a conversation about that. This is also from my colleagues at Microsoft Research and his collaborators. But at the same time, I want to go back to my first sentence in the talk because I want to raise more questions than answers. So let's take our running examples for Lava and see how things are. The red boxes shows, first of all, the caption generated is much better than the previous captions that I showed you. It's more rich, it's more descriptive and such. Then at the same time, let's read it. The image features a group of people standing in a circle, all smiling, looking at the camera. There are at least 9 people in the group, which is great. It has done a good job at counting, which sometimes it does, sometimes it doesn't. I try to try it a few times, so it's stochastic. Take it with a grain of salt. With 7 of them wearing ties, there is no tie. The group appears to be posing for a photograph. They are not. Possibly in a professional or formal setting, the people are all facing the camera, they are not. Showcasing their friendly and happy expressions. I don't see happy expressions here. And, you know, as you see, part of this could come from the vision side, but part of this could come from the LLM because it doesn't know what should we pick, what should it pick, what should it not pick. And the model still totally loses the point that, you know, there are those two people looking at each other. And let's continue. So where did the man and the woman looking at each other did they graduate school? And I think they did at University of Wisconsin. But I checked, you know, so basically, none of them has attended. They're very well-known, you know, actors and actresses, but none of them attended the University of Wisconsin. You know, and then asking who they are, the man and woman looking at each other are a couple. They are not a couple if you have watched the movie, you know. And they are both wearing ties, which they are not. They could be the host of the gathering, which we don't have any information about it from a single image. Or possibly the parents of the child in the group. So if you take a look at the child in the group, even the race is not the same as the two people. So that's also wrong. And how old is the child? So it, you know, it has estimation of the child is between 4 to 10 years old. So should we allow the models to generate those estimations or not? That's a separate question itself. And where is she, by the way? The small child is in Japan. So that's correct, because if you have seen the movie, it happens in Japan. But how the model figured that out, that's also a question. And
well,
I'm well over time, so I don't cover.
Excuse me for a second. Well, we have coffee break until 10:40, but because I think everyone is really interested in this talk, so we'll just go on. But you can have a coffee break if you need to, and also we are having a poster session. And poster session is also was scheduled for the during the coffee break, but well, I think we got extended to 12:00. So I just want to say let's keep on going.
I can stop here because, you know, the last part was if time permits, but
yeah, if you have 10 minutes.
You want me to talk now? Okay,
Yeah.
sure.
We're enjoying it.
Yeah, you have 10 minutes.
Yeah, so the last part is actually the recent work that we did. So the first image in my slides are generated by DALL-E. So these text-to-image generation models are actually becoming quite good. And they're relevant to image captioning as well, because, you know, the sort of if you understand them well, we might be able to gain more by creating self-consistency loops. So here, this was a work that I did with my intern, Tejas Kohale, last year, the summer, which basically the goal was to see how good the text-to-image models are in terms of very simple relationships, left, right, top, below. That's it. So nothing more complex than that, but just let me walk through this exercise that we did to just understand how important is the evaluation for this one. So first of all, this is a bit of interesting observation, which we have all observed that, you know, this is where we were at 2016. And these were, you know, CVPR papers, ICMR. We were very proud of these results, but suddenly in 2022, you know, all these text-to-image models came. They're wonderful, and there have been huge progress there, thanks to the scale and the wonderful work that the creators of these models did at different companies and institutions, and especially thanks to those that make them open source for the community to use. Now, if you take a look at the metrics that are used for this task, they're usually based on the FID or inception score, and if you take a look at that, it's based on the classes in the image net. and measuring what is the similarity between the features created by the image during training and those classes. That's a separate discussion, how comprehensive are the classes of ImageNet. But there is another one, our precision, and here I have just listed them, and also on the top we see the models that they have used them. As you see, everybody is using inception score. But there have been some works using like image captioning metrics as well to measure the quality of the image, basically because you can generate the image, can generate the captions and such, and also the key score using these pre-trained models to measure the similarity between the text and the image. And also, another word, SOA, semantic object accuracy. So as you see, I've listed the 4 categories, which is either purely visual metric for photorealism, which is actually working great in the pre-trained models that we saw. Image text matching, object level metrics, and also some limited human studies. And this is just motivation. Spatial relationship is important in different applications, so is important to consider about it. But many of them are not effective as we look into them. For instance, this is the example of clip score, where we have an image and the text is backpack below a train. The clip score is 0.86, and a backpack above a train, clip score is 0.87. So it cannot differentiate because it has not been trained to do so. So it cannot differentiate between the spatial relationships. And the same for the second example, as you see. And we have observed similar behavior from other metrics. So we created this very simple metric, which we refer to verifying the spatial object relationships. Which basically it uses, it could be any object detector as a proxy. You can take any one which we took one that was open source and isn't very good. And having a templated data set of, a list of objects, we started with the COCO and, templated things to generate thousands of those templates with the object names and the relationships, currently covering 4 relationships. And then having each of these models generating 25,000 images. And we ask each model to generate an image 4 times. And we measure the success rate based on if it gets things correctly for all the occurrences, 4 times, 3 times, 2 times, 1 time. This is like a blue 1, blue 2, 3, 4. And to our surprise, as you see, the performance of the models are actually quite poorly for this. And that's natural because the models are not trained to track this. They're basically measured by FID. And if you optimize for this, we don't know, maybe the quality of FIDs will drop. But this is important to, again, go back to the point that Anna mentioned in the first talk, that the utility, what do we care about when we build these models? And, it's great that we build these models, but it's important to spend time to, do the meaningful evaluation for them. And yeah, this is my last slide. So this is what Tejas sent me. There is a skateboard below a mouse. And as you see, the dolly thinks it's a computer mouse, stable diffusion thinks, and this is a version, the first version, that it's a picture of it on a skateboard. So, as you see, there is a lot that we don't understand about these models. So we don't know why stable diffusion thinks it's the animation of the mouse, but the dolly thinks it's an actual mouse. But if you give the right context, like the couch, it is actually an actual mouse. And that's all I have for today. Thank you for listening to me.
Very entertaining. I love the research that you did around that picture. Question. Please. You have a big voice, so maybe they hear you.
All right, thank you very much for the nice presentation, Hamid. I want to congratulate you to achieve the first objective. At least for me, you raised more questions. So on that note, I just wanted to pose another question to you. So you talked briefly on the hallucination part, right? Have you completed the loop that from image going to text and then from text going to image and then having adding another generative model to actually translate or transform the text to the image and then running your metrics on top of those? Would that help even?
That's a very good question. We have not done that, but having these self-consistency loops between the models, it actually is very, very promising. And one example for that is the GPT-4 example that we have seen that when the model has been given the opportunity to do discrimination tasks during generation, meaning that it generates a sentence, it is asked about a specific aspect of the sentence, and asked to generate again and do it again and again. It improves things, so most probably it helps, but then it comes to the question of how do we evaluate hallucination. So what type of benchmarks we look into, what we measure, and how do we balance things between creativity and factuality.
Excellent. Thank you again, Maria. It was really amazing. We release you for the coffee break. If someone else wants to ask questions, please come forward and we'll continue to have some questions for others. Okay, thank you for joining. Come back after the coffee break. We have another set of amazing speakers.
Oh, well, our original session was scheduled to start at 10:40, but it's already 10:40, so we will have a short 5-minute break and start the next session.
Very good.
Thank you.
Thank you.
네. 아, 그 홈페이지에 있어요. 저희 페이지. 네. 페이지에 삽입 누르면 바이오 써요. 네, 그렇게. 페이지에 사진 오늘 보내달라고. 대기시상이요? 네. 원래 1위 수상자 주는 거라. 사진이 없으면 1위가 없으면. Shangyu, are you still there? 마지막에 단체 시상 사진 찍을 때 이야기할게요. 지금 메일 보내가지고 그때 카메라 좀 켜달라고 이야기할게요. 예. 네, 알겠습니다. 그래서요, 거기 순서 적혀있는 12시에 딱 끝나나요? 더 늘어질 수도 있고 12시에 늘어질 수도 있고 11시에 나가면 한치사시라고 지금 찍으면 아, 어차피 시장 때문에 요 순서인데 또 노아가 안 왔어요. 네, 그리고 학생이 계시는 게 Oh, yeah, I'm here. Oh, cool. No, yeah. Oh, it's 10. It starts at 10:40. You're the board. Yeah.
Can I check the?
Yeah, sure. 체크했어야 할 거고 그다음에 선생님과 내려오래.
そう、なんか一回高速で読んでも無理だったんですよ。なんか高そうかな。これどうやってやればいいですか？これズームでやって
So are you?
Just starting this morning with Stephen. I don't know if you know this specific person. I should give the name. Oh, sorry, this is person. I'm sorry, but you have the same interface. And do you know her? She's the author of this. No. Let me check. But yeah, let me check. Let me
We'll start our second session.
Right. So welcome to the second invited speaker session, nice workshop. We have 4 talks in this session. The first speaker is Professor Noah Garcia, but unfortunately she cannot travel to CVPR. So on behalf of her student, Yusuke will present. Please welcome.
Hello everyone. I'm Yusuke Hirota, PhD student in Osaka University, working with Noah. I'll be delivering this talk instead of her as she had a baby recently and couldn't come to CVPR. One of our research interests is vision language. We believe vision language offer a unique and interesting field of study. Some of the reasons are it follows well the intuition about how humans interact with the world. We mostly perceive the world through vision, and we mostly communicate to the world through language. Because of this, it is thought to be a good benchmarking test bed for reasoning skills, or at least some level of semantic representation between multiple modalities. So it has been shown to be very useful for pre-training large models such as CLIP, as image text pairs can be kind of easily scraped from the internet. As we all know, vision language has made outstanding improvements in the recent years. We can see it by just looking at the readable of VK 2.0. Especially with the use of large pre-trained models, the accuracy has been boosted, not only for VQA, but also for vision language tasks in general. However, while we measure a task success according to accuracy metrics, other things that we are not measuring are happening. For example, in the left caption, a model generates the word man when placing the attention in a computer, even though the person in the image is human. Or the model in the right adds racial related words to a caption that are not present in the human generated caption. As isolated examples in the slide may not tell you much yet, but yes, somehow So it looks like there may be a problem with bias in our models. We can naively think that as soon as bias is detected, it can be solved. So then it's not a big deal. We can also naively think that we are learning from our mistakes. And eventually, these types of behavior will disappear from our models. I want to show you this news report from July 2015. And this, the other one from September 2021. 6 years apart, exactly the same problem happening. So it looks like bias will not be solved by its own, and we need to put our resources and effort to prevent it. To start studying bias, we first need to understand where bias comes from and how societal bias is incorporated at different stages of our overall frameworks. So everything starts with the real world. The world has some historical discriminations that affect multiple aspects of our society and people's life. We take images from this imperfect world, maybe share them online, and images online are used to create datasets. Each of these steps is affected by selection bias. That means that we have some biases about what we take photos of, what we upload to the internet, and what photos are used to create datasets. As we add human annotations to the dataset construction process, this introduces annotation bias. Then, algorithms not only are trained on this bias data, but also they can amplify the bias due to the algorithmic bias. Finally, as models are used in applications, the bias is introduced back into the real world, reinforcing historical discrimination. Our work has focused on studying bias both in our datasets and models. Last year, we presented a new metric to measure bias amplification in image captioning. So let me first introduce what is a bias amplification. Let's say we have an imbalanced dataset in terms of gender with 70% men and 30% women. And we train a model on this dataset. What happens quite often is that the prediction of the model are even more imbalanced than the original datasets. This is called bias amplification. Our metric called LEAK is designed to measure bias amplification in image caption models. We start with the assumption that if we can train a classifier to accurately predict a protected attribute of a person, for example, the gender, from a neutral caption, then the data is biased. So we input captions in a language classifier to try to predict, for example, the gender or the race. In this example, the classification will be trivial because we have the word boy, which reveals the gender. So we mask words that can reveal the attribute to the classifier to make the sentence neutral. And then with these masked sentences, we can measure how confident the classifier about the attribute of the sentence. We call this bias score. Here, there is an overview of how we compute bias amplification in the case of binary gender. For the image set with gender annotations, we have the self-human captions and the self-generated captions by a model. We mask the gender revealing words for all the captions. And then we train two different classifiers. The difference in accuracy between the classifiers is bias amplification. So let's see what this metric can tell us. First, we found that all the image captioning models we tested amplify gender bias. Another finding is that the equalizer model, which was designed to mitigate gender bias and successfully reduce gender misclassification, actually amplifies bias with respect to the baseline in the leak metric. We investigated why this happens. In this example, the equalizer is fixing the gender misclassification with respect to the baseline. But because it's not looking into the rest of the sentence, what it actually happens is that the gender prediction makes the model predict gender associated words in the rest of the sentence. In this case, the misclassification and the leak metric are complementary. When measuring bias amplification for skin tone annotations, we see again that all the models amplify bias, but it's smaller than gender bias amplification. With these insights, our next step was to work on devising image captioning models. We are presenting this work here at CVPR on Wednesday, so please come by if you're interested in more details. And based on the observations in previous work, we hypothesized that there are two different types of biases affecting image captioning. First is context gender bias, which makes models exploit the context of an image and presently generated words, increasing the probability of predicting certain gender. Second is gender to context bias, which increases the probability of generating certain words given the gender of people. In this work, we propose a framework called Libra that mitigates bias amplification in image captioning models by considering both types of biases. The idea behind Libra is as follows. A model trying to correct both context to gender and gender to context biases in captions will be able to amend these biases in any captioning model's output. So our proposed Libra is model agnostic, which can be applied to on top of any captioning models, and also it mitigates both types of biases. Specifically, Libra consists of two main modules. The bias caption synthesis, which synthesizes captions with context to gender and gender to context biases, and devising caption generator that mitigates gender bias in the input caption. So we evaluate gender to context bias of various captioning models before and after applying Libra. The results show that Libra mitigates gender to context bias in all the models. We also evaluate context to gender bias. The results show that Libra mitigates context to gender bias in most models. We show some examples that Libra mitigates gender bias. As for gender to context bias, Libra tends to change words skewed toward each gender to less biased ones. For instance, in the left caption, in the left example, the baseline produces the incorrect word suits, which is skewed toward a man in the dead set. Libra changes the word to the more neutral one, jacket, mitigating gender to context bias. As for context to gender bias mitigation, Libra can correct gender misclassification even if the context is skewed toward the other gender. For example, in the right sample, the baseline predicts incorrect gender, man, probably due to the male-skewed context surfing. Libra predicts correct gender, mitigating context to gender bias. We compare Libra with other bias mitigation method, equalizer. Equalizer is a bias mitigation method to force the model to see people in the image to predict correct gender and successfully reduce gender misclassification. Whereas equalizer generates a woman skewed word, bikini, at the expense of predicting the correct gender. Libra predicts the correct gender while not generating gender stereotypical words. Next, we studied bias in datasets, in particular in visual question answering datasets. It is well known that VK models suffer from statistical bias. For example, if all the bananas in the training data are yellow, when the model is presented with a green banana and asked about its color, it will answer that the banana is yellow. This means that if the data in a training dataset is unbalanced in terms of, for example, race or gender, we'll be producing unbalanced models. So we investigate gender and racial bias in 5 major VQ datasets. Regarding gender bias, by looking into the number of samples per gender, the first observation is that men are overrepresented in all the datasets, appearing in twice the samples than women. Then we compare the top 20 most frequent answers for women and for men questions. There are many answers that are similar, like the colors, but when looking at the answers that are different, we can start to see some trend, and it is that the answers related to sports only appear in men questions. So the conclusions are that all datasets are imbalanced, that the answers are different according to gender in the questions, and that we found some problematic samples. Next, we analyzed racial bias. The frequency of the answers for the racial question is also very imbalanced. For example, white and Caucasian appears 3.5 more times than Black or African. Similar to gender bias, we found that race in VK datasets is imbalanced. Another observation is that race and nationality are described from a US point of view. Finally, we also identified problematic samples with negative connotations for some groups. So in our last work, we analyzed the bias in large scale and uncurated image text datasets. We are also presenting this work here on Tuesday, so please come by if you are interested in the details. It is known that even small but manually annotated datasets are affected by societal bias. And this problem may be getting worse with data pulled from the internet. These large and uncurated datasets stimulate models being trained on hundreds of millions of samples. However, the larger the train set, the less control over the data, leading higher risk of societal bias. The contribution of our work is to annotate images in a large-scale visual language dataset, which is Google Show Captions, to facilitate analysis, evaluation, and mitigation of bias in visual language tasks. So from our analysis of the 6 annotated attributes, we found that all the attributes are imbalanced and skewed towards certain dominant classes. For example, as for age, the predominant class is adult, while for gender, the gap between man and woman is huge, and it's bigger in skin tone and ethnicity. As for the emotion attributes, the most represented emotion is neutral, followed by happy. To further explore the data, we cross-check gender with emotion attributes. By analyzing the gender emotion correlation, we found that women tend to appear happy, whereas men tend to appear neutral. With our annotations, we evaluate societal bias in vision language tasks. We evaluate image captioning models, OFA, and CVPR with leak metric. Our results show that both models amplify bias with respect to the original dataset, excluding OFA in skin tone. Lastly, we analyze demographic representations on stable diffusion. Use a caption that come with each image in the GCC dataset as prompts to generate an image for each original image in GCC. By analyzing the generated images, we observe that gender-neutral prompts often result in images predominantly depicting white men. So that's the end of the presentation. Thank you for your attention, and please visit our posters for more discussion about or questions. Thank you.
I actually have a question. So at the end of the talk, I mean, almost the end of the talk, so you mentioned that the bias issue can be more amplified in the large scale data set. So is it confirmed by your experiment or just conjecture?
It's kind of the rough assumption of bias, but we conducted some experiments like in the downstream tasks in image capturing. For example, in this example, the models are trained on the large scale dataset GCC, and they amplify bias in terms of gender or any other attributes. But we haven't compared with the influence between the scale of the dataset, so it's kind of the future work.
Hi, very nice talk. I'm wondering a question about the motivation for balancing the data set. Because I mean, I understand the need to balance it because the model will learn from a balanced data. But the data distribution of the world that you're learning from is unbalanced. So there should be, rather than balancing the data set, there should be a method to fix the outputs, not the inputs to the model, right?
Yes. And I think you were talking about the devising paper of image captioning.
I'm talking about the VQ work.
VQ work. Okay. Okay, so yeah, I agree with you. And in the VQ work, we just like investigated the distributions over race in terms of race or gender. And yeah, and even if these kind of distributions are balanced in the dataset, I think the model will amplify bias because it like the context in the real world is kind of very skewed towards the gender. So
right. So I'm saying that this is probably a problem in general, right? Independent of bias, like bananas or other. Yeah. So instead of looking at the input distribution, isn't it better to determine better loss functions or better methods of training?
Yes, maybe, yeah.
Thank you.
Thank you.
Right. No question. All right. Let's finish the first talk. So keep the time to. Thank you. All right. Second talk of this session is will be done by Jack Hassler. So actually, they were scheduled for Kudelia Schmidt, but Kudelia had a talk in the first session. The Jag is a research scientist in AI too, and he is going to talk about. Sorry. Yeah, the question is not enough for image captioning. Please welcome Jack.
Great, are we all set? Awesome, yeah. Thanks so much for the intro, and thanks so much to the organizers for inviting me. And yeah, I'm super excited to be here today to talk about why recognition isn't enough for image captioning. This builds on some themes that were discussed in the prior talks, but hopefully you'll indulge me in my take on this. Right, so the big takeaway from my talk, if you get nothing else, is that image captioning is not simply pasting objects together. I think most people in this room believe that, but maybe some other folks who are not in this room still need to be convinced. But consider the following set of objects. We have, I guess, 4 people and a windmill in the center of them. So think for a moment the type of scene that might give rise to these objects. You might be thinking of, the Dutch countryside and people standing around some windmill. You might be thinking of, a, I guess, wind turbine or something like that. And you might generate the caption, a group of people are standing near a windmill. So this is pretty good given the information I've provided, but consider the following image, which also surfaces this particular set of objects. So here we have a very complicated scene, which indeed is a group of people standing near a windmill, but this caption is entirely useless because it misses the point of this scene. So take an extra moment to parse the scene. There's a lot going on. I'm going to show you a caption that I don't think is a perfect caption, but I think is nonetheless more descriptive of this particular image. It looks like a husband set up some type of mini golf surprise party in the backyard for his wife. So we're going to break this caption down a little bit. And again, I don't think this is a perfect caption, but it's nonetheless one that someone wrote about the scene that I think is more detailed. And I think we can all agree that we can at least see where this caption is coming from. But if you start to break down the sort of reasoning that's required to arrive at this caption, things get really complicated really fast. So the first thing that we might need to do is run some sort of recognition mechanisms. And so perhaps we have to, detect the major actors in the scene, and we might need to perceive their gender and their age. We have this really interesting windmill. So probably this isn't the windmill that any of us were thinking of when I just said windmill. This is actually like a mini golf windmill, I guess. So it's sort of this compound object. Do folks play mini golf? I actually haven't played in a long time, but I think this is a mini golf windmill.
Looks like it.
Looks like it. Okay, yeah. And crucially, we also have this blindfold that's adorning this woman. But even this isn't enough. So we have to start doing some deduction on top of these detections to start getting to the content that would be required to generate this caption. So we see that only this one person is wearing a blindfold. So this is how we infer this may be some sort of surprise. Perhaps everyone else is in on it. Oh, and by the way, this man standing here in a suit, we've assumed that he set this up based on how he's framed and how he's standing. Oh, and also, we perhaps assumed that these 2 people, the shorter ones, are first kids, and also perhaps this couple's kids, maybe, unclear. So all of this had to happen in the blink of an eye before we could generate this caption, and yet I would argue this process is more effortless than it is, effort to write down all of the steps involved here. Good. So. To summarize, we need all sorts of really fine-grained detection mechanisms. So an emotion detector, open vocabulary object detector with this windmill, blindfold detector, yada, yada, yada. And on top of all of this, we need a reasoning module to start making inferences about this scene. By the way, we can't be sure about 100% of these details, right? So I've just shown you a picture, and there's a lot of assumptions buried in the sort of reasoning that we're doing here. So we've assumed the genders of these people, we have assumed their ages, we have perhaps inferred a relationship type, and as a result, one thing I like about this caption is that it doesn't represent these inferences as 100% definitive. It surfaces some uncertainty here, which I think is nice. Oh, by the way, if you pass this through a state-of-the-art object detector, this is one that's trained on LDIS, which is a really large vocabulary classification data set, you're going to get a lot of objects. I think the max output by the detector is 300, and I think 300 objects may actually be here if you count all of the stacked on top of each other ones. And again, ignoring the accuracy of these things, which is not 100%, which of these details are salient? Like certainly bigger objects are salient, but like, I don't know, we really needed to see that blindfold, which takes up a really, really small amount of the pixels here. So this is a lot, and it's just one scene. And every scene I could walk you through in any given data set, and I could probably give you an argument that to really understand these scenes, we need something beyond just recognition. And so again, short version is to generate useful and accurate captions, we need better visual common sense. And that's what I'm going to be talking about today. So I work at AI2, and our group studies visual common sense. So I'm going to talk about 3 different types of visual common sense reasoning that we've been working on in recent years. The first set of projects I'm going to talk about deal with temporal reasoning. These are projects that were first presented at NeurIPS a few years ago, and then at CVPR last year. Joint work with a lot of awesome collaborators from AI2 and the University of Washington. So it turns out, as perhaps some folks in this room can attest from firsthand experience, models are pretty bad at zero-shot temporal reasoning. So if you take this data set from Huang et al., this is the visual storytelling data set. This data set couples sequences of images alongside sequences of captions that together tell a story. And you ask a recognition style model to order the images of the story. It makes mistakes. So here we have this cute story of an older man, I guess, going up an escalator to meet his kids at the top and then getting on a bus. Very wholesome. But if you ask Clip to order this story, it turns out that it says the man gets to the top of the escalator prior to writing it, which is not the order that I would choose or this annotator chose. So yeah, our models are fairly bad at zero-shot temporal reasoning, at least Clip is, and several others that we tested as well. So how are we going to fix this? Well, like one of the speakers earlier in the sessions, we are going to try to learn a temporal understanding of the world using web videos. So the game plan that we have is we're going to go out, we're going to collect a lot of web videos, in this case from YouTube, and we're going to apply the standard sort of pre-training framework of training a giant vision language transformer on this data and hope that we can get the right mix of modeling objectives and model components to actually capture temporal understanding in a zero-shot way. So yeah, this is what we did, and our model is called Merlot. I won't get too much into the nitty-gritty of how this works, but basically it's a joint vision and language transformer, so fairly standard architecture these days, trained on 3 different pre-training objectives. The first 2 are contrastive frame caption matching. So this is sort of the Clip style objective where you're trying to assign a high similarity score to truly corresponding images and their associated ASR while minimizing the other ones. We also have the classic BERT style mass language modeling where we mask out a word and ask our model to predict that missing word. But finally and crucially, we have this temporal ordering objective where we take 2 frames from the video, and half of the time we put them in the correct temporal order, and the other half of the time we flip them, and we have the model differentiate between these 2 cases. The hope here is, again, to learn in a zero-shot pre-training style way a temporal understanding of the world from web videos. So how do we do? Oh, yeah.
Did you say you reverse the entire sequence or you flip it there?
Yes, so Merlot actually only operates on 2 frames at a time. So this is a great question, yeah. So half the time the frames are correctly ordered temporally, and the other half, yeah, good question. Great, yeah, so how do we do? Well, for zero-shot temporal reasoning on that same data set I mentioned earlier, we outperformed the baseline. So this is a pretty good starting point indication that we're learning something new, at least compared to these models here. But beyond that, we also fine-tuned for downstream tasks. So we, at the time, set SOTA on, I think, like 13 different QA-style tasks that presumably require temporal reasoning. So these are things like TV QA, for example, which is question and answer pairs over movies. And the example on the right is from the VCR dataset, the visual common sense reasoning dataset, which I'll return to a bit later. But again, this is sort of like a QA task. So yeah, we got state of the art on these tasks, which I think showed that we were really learning something new above and beyond the models that were available at the time. But this wasn't quite enough for us. We had this big, pre-training corpus of videos, and we wanted to go one step further with this. So in follow-up work, we took the additional step of adding the audio modality here. I know that some folks here maybe have worked with audio as well, and this was an interesting first foray. So what we did was we modified our pre-training objectives to account for this third modality. And I think two-modality pre-training is already quite difficult. Like you always have models trying to shortcut and ignore the image or ignore the text or whatever. With a third modality of audio, things get even more complicated. And yet we were able to come up with a balanced set of training objectives that models couldn't cheat, essentially. We also expanded our pre-training corpus. We expanded our model compute, and we trained for much, much longer. Again, our zero-shot reasoning capabilities we think are very strong. So here are some numbers. Higher is better for all of these things. I won't talk about all of them in detail, but one result I will highlight here is that for situated reasoning, we were actually at the time outperforming the supervised state-of-the-art using this pre-training approach. So we were super happy about this. So I think that's all I want to say about temporal reasoning. So again, we were pre-training from web videos, which I think is a really promising direction going forward. Next, I'm going to talk about some work that we presented at ACCV this past year that deals with abductive reasoning. Abductive reasoning is the process of forming explanatory hypotheses about a messy and incomplete situation. So given an image, say the one that we examined earlier, we can't be 100% sure of a lot of the details that we're inferring, and yet we're still able to reason on top of that in an honest way. And this is what this data set aims to embody. This is a joint work with a lot of awesome collaborators, including Anya, who gave a talk earlier today. So to be very concrete about what we did, we adopted a free viewing paradigm when we were collecting this data set. First, we showed crowd workers images with no additional context. So this image, for example, was shown to annotators, and we had them first identify salient clues within the image that tell them something interesting about it. So here are the clues that the annotator highlighted. The one that I'm going to talk about most is this sign, a sign with words in a language other than English. So given these concrete observations, we then tasked the annotators with making inferences about these observations that go beyond the scope of the image. For example, for that sign, the annotator wrote that it's possible that this is in Spain. Now, again, we're in this inexact realm of abduction. So we can't be 100% sure that this is in Spain. There's lots of countries that have signs in Spanish. Spain, Mexico, Canada, US. I would argue probably most countries have a sign in Spanish. So again, we cannot be 100% sure here, but the goal of this data set is to study the sorts of inferences and assumptions that people make about scenes.
Sorry,
oh yeah, sure.
So they were supposed to look for things that would hint at something interesting.
Exactly,
right?
yeah, free viewing.
So if you're in Spain,
yeah,
that wouldn't be interesting.
That is true, yeah. So these are context free. So we just plop the annotator down in whatever scene they see, and they tell us what is interesting about it. And we think this sort of free viewing paradigm hopefully will give us one particular view of the set of images. But yeah, this would not be so interesting if you were in Spain, perhaps, yeah. Or maybe it is, maybe you want to shop at Santos, I don't know. Right, good point. So yeah, context-free free viewing collection. We really scaled this up. So we collected 363,000 clue inference pairs situated in 103,000 images, compared to prior data sets that may cover similar abductive reasoning paradigms. We have better coverage. And we trained a model on this data set, and here are some example predictions of the model. We have a sort of highway scene here, and we also have this bar scene. And the model makes some pretty good predictions. So if you look on the right, you can see that there's this like flower bouquet and this little like statue here. These are poinsettias, which in some places are traditionally put out around Christmas time. And that is what an annotator actually said. And indeed, our model makes the prediction given this context. It is the holiday season. So we're seeing some interesting abductive inferences here. Things aren't perfect though. So here's some error cases. My favorite one here is in the upper right. We have this very interesting boat with some flowers on the front. It may be too small to see, but there's this sign that says like flowers for sale on it. And humans agree that this is probably some sort of unique florist shop. Machines can't quite make that inference yet, probably because they've never seen a florist shop on a boat like this. So speaking of error examples, we have a leaderboard, and we've been really excited to see the uptake in that leaderboard. I think we're above 70 submissions now. So yeah, thanks to anyone they've submitted to this leaderboard. There's still a huge gap for a lot of the tasks that we pose over this corpus compared to the best machine performance and human agreement. So lots of headroom here, and our data set is available. So yeah, good. So I think that's all I'm going to say about abductive reasoning for now. I'm going to move on to the very final part of this talk, which deals with some ongoing work regarding uncommon sense reasoning. So this is, again, joint work with awesome collaborators, including Ludwig, who I believe is giving the talk after this. So fun to see some familiar faces around. So yeah, so what is this new data set we collected? We collected a data set of unusual images. So we went out to the some Discord communities that house designers and artists, and we got them to generate some unusual images for us. Here is a sample of them. I think my favorite among all of these is the lion eating the carrot. The carrot's a little bit wonky, so you can see some of the diffusion processes not being perfectly exact here, but nonetheless, the point here is that the lion eating the carrot is unusual because lions are carnivorous. I think that's true. Yeah, lions are carnivorous. I'm going to say that and make that claim. And this is why this is an unusual image. And we have similarly unusual images that embody different types of common sense violations in our corpus. The difference between this type of data and most visual common sense setups, such as VCR, which I mentioned earlier, is that we cover a different part of the input space compared to prior work. So a lot of these visual common sense data sets usually depict some normal scenes. So like something normal is happening and you get a question that's like, what will happen next? And you have to predict a very normal thing. We cover a part of the input space dealing with unusual scenarios and instead flip the task on its head to task models to reason about why something is unusual. Which you'll see they're not quite so good at yet. Oh, by the way, we're not the only people interested in these sort of uncommon sense questions. Seeing some laughs around the room. So we put this on archive, and then GPT-4 came out on archive, and we were sort of shocked to see that their figure one for their vision backed GPT-4 model is actually uncommon sense images. So clearly, we're not the only folks interested in these images. Yeah, I think the image on the right somehow is the demo image for all of these new GitHub models. Looks a little bit dangerous, but anyway, so what do we do with the corpus that we gather of these uncommon sense images? The first task is binary classification. So given two images that depict very similar content, only one of which is unusual, can the model discern which is unusual? In this case, the Rubik's Cube on the right is very, very difficult, maybe impossible to solve because this extra purple square is on the top and you cannot solve this Rubik's Cube. So we have a binary classification task, and then we also have a free text generation task of explaining why an image is unusual. Here is a more verbose explanation of what I just shared. So how do models do at this? Not very well, not random, but not very well. So if you take Flan T5 XXL, which is a sort of off-the-shelf, really strong vision and language model that hooks into a large language model in Flan T5, you can see some of its predictions here. So Flan T5 11 billion says Rubik's Cube is made up of 6 identical squares. That is kind of true. Like I can kind of see what it's getting at, but that's not really why this is unusual. So you're kind of not doing so well. And indeed, on the binary classification task, we see a big gap, and on the explanation task, we see an even bigger gap according to human rating of these generated explanations. So models these days, at least the ones we considered in the paper, really don't understand these uncommon sense images at all. And we also have some additional uncommon sense image benchmarks that we're building out as well that I unfortunately don't have time to get to in this talk, but I'd love to chat more about. Cool. Oh yeah. Like all of the other data and models that I've talked about today, everything that we do at AI2, we try to make as public as possible. So for the Whoops benchmark, yeah, you can go download it and play with it if you're interested. I'd love to see what folks build with this corpus. So yeah, just a brief recap. I think I'm very out of time. Today I covered 3 different types of common sense reasoning dealing with images. And I started out by arguing first that we needed better visual common sense to generate accurate and useful image captions. And so, yeah, thanks so much for coming, and thanks to the organizers for inviting me. Yeah, thank you.
From audience.
Okay. I'll ask a question.
Oh,
hi.
Hi there.
The uncommon sense. I was wondering if we can build models that can get good at uncommon sense. Can those models then be used against us in trying to describe something that has no common sense base, but giving reason why it could be possible, creating even more inconsistency between truth and what we can certify as legit versus what we can believe that it's a possible explanation?
Yeah, that's a great point. So the idea that if a model got very good at this, it could explain any situation, even ones that are maybe purposefully or maliciously designed to be confusing. Yeah, I think it's a risk. I think that I think that developing detectors for this malicious behavior can happen in step with detecting better generators. And I think what our probes are showing is that we're definitely not there yet. So yeah, I'm hopeful that these uncommon sense models can both serve as a probe to see how close we are to this bad scenario, but also eventually, if we are in this scenario where models can do it, as detectors of potential malicious behavior. Yeah, it's a great point though. Yeah.
On the loops data set.
Yes.
Those were AI generated, right?
Those are they are AI generated images. They're generated in collaboration with some designers and artists who spent a lot of time, and we were working with them quite closely actually. And yeah, so it's sort of a collaboration.
Did you have to work hard? Like for instance, you could say that carrot picture was wonky.
Yep.
Because the carrot was round.
Yeah. So
that's not what you meant.
Yeah, exactly. Yeah. So I think this brings up a lot of amazing points. Like, what is the intent of these images? Like, what is unusual about them? The carrot is a great example.
Or like a lion wouldn't pose for a picture.
A lion wouldn't pose for a picture. A lion wouldn't be over a backdrop, that's like very well staged. There are all sorts of unusual things that happen, not just in these images, but also, I guess, in like pretty much any image. Like if you really look at these examples, even from MS Coco, like there's a lot of weird stuff in there. And I don't know, I think, yeah, in our human evaluations, we didn't give the people the prompts, so they didn't know our intent with what was unusual. They just got a machine explanation of what was unusual. So those evaluations could account for that. But I think your question brings up a really nice point about like, yeah, what is unusual? Yeah, it's a good question. Yeah.
Sorry, one more question.
Oh yeah.
I was curious, kind of tying to the previous talk as well. Common sense could also be cultural, or there are biases there as well.
Yeah.
So, in your evaluations, what kind of annotators do you use to care to make them diverse or?
Excellent question. Yeah, so this is so for this particular set, the annotators, I believe, are drawn from the same pool of folks who are making them. So we never let people annotate their own designed images, but it's still this set of designers, which, yeah, these Discord communities have their own, demographic distributions and biases. And this is something that, in the future, we really should account for, because what is unusual to one is usual to another. Yeah, I think this is something that I think about a lot, particularly in dealing with the abductive reasoning. Like all of these inferences we're making about scenes, like unless they're very, very literal, have assumptions baked into them. So sure, there's a cup on this table, but like, I don't know, like even this benign scene. See, I was even actually looking at the other cup. Sorry to single out the cups here. They're just the first thing that comes to mind. But yeah, like I think we bring our own both implicit and explicit biases into these annotations, and we're hopeful that we can study these biases without endorsing the outputs of a model trained on them necessarily. But I think it's a good question. We should think more explicitly about it going forward. Yeah.
Thank you.
All right, thank you so much. And thank you.
Ludwig Schmidt is supposed to give us a talk, but he didn't show up. So we have to move on to the last one. The last talk, I'm not sure, so it would be maybe shown later so that then we can, have another talk, in this session. Okay, but this talk will be given by the Hong-Nam Lee. The Hong-Nam Lee is an associate professor at University of Michigan. At the same time, he's also the senior VP and chief scientist in LGAI research. Please welcome Hong-Nam.
Okay, I'll start. Morning, everyone. Thanks for attending this workshop. So throughout the workshop, we have covered various aspects of image captioning research, what our needs have achieved so far, what our current problems are, what we can do, what we can do to solve more. And in this talk, I'll briefly recap some of the history of image captioning, along with what LGA research has been working on. I'm also going to talk about what we have learned from the NICE image captioning challenge and share our thoughts on zero-shot image captioning. So like other fields of computer vision research, image captioning has gained popularity since the appearance of MS-COCO dataset. MS-COCO image, as we all know, the captioning dataset consists of 150,000 images with 5 captions for each image. And in addition to MS-COCO, several other data sets have been proposed. And for evaluation of these captioning performance, various methods like BLU, McCare, Rogue, CIDR, SPICE have been proposed. So together with these data sets and evaluation metrics, they have been instrumental in driving the methodological advancements and also progress in image captioning research. And as we all know, in this NICE challenge, we have investigated a new zero-shot image captioning task using high-quality, diverse images and descriptions sourced from Shutterstock. And I'll briefly talk about some of the models for image captioning. So most widely used image captioning models utilize vision features from object detectors to make a model understand an image. For example, OSPAR model from Microsoft uses object tags and vision features from object detector as the input to transformer architecture to generate captions from an image. Different from previous models, our team in LGA research has proposed to use embedding vectors from an autoencoder to encode images. The model called ELVERS, which was proposed in CVPR last year, utilizes BQVAE to encode an image into a sequence of embedding vectors. And using the sequence of image vectors and text, we trained the autoregressive transformers bidirectionally to form a powerful and efficient image captioning model. And based on ELVERS, we further trained the same architecture on 100 million curated image text pairs to enable zero-shot image captioning. And this model, which we call BITRS, is also a base model for our XL1 multimodal image captioning framework. Trained on high-quality curated data set from Shutterstock, the BITRS model can generate accurate captions for various types of images, including natural photos, studio shot, vectors, and illustrations. The model not only generates captions, but also keywords for the given image, and they can be useful for image search and tagging. We'll be presenting more examples in the Expo booth, so please check them out if you're interested. Concurrent with embedding-based method, integrating frozen image encoder with large language model also has gained its popularity. One of the most popular examples is Flamingo from DeepMind to link frozen vision encoder with frozen LLM to enable a few-shot image-to-text generation, and it includes captioning as a task. So thanks to the advancement of image captioning technology, we are now able to do many useful things. For example, aiding visually impaired people with everyday visual challenges, or explaining an image with language-based AI models, and improving image-to-image search with alternative text, and improve identification of hateful content on the web. However, some questions I like to think of are, is describe an image in a few words enough? And another maybe more important question is, what does it mean to perform well in zero-shot image captioning tasks?
So traditional image captioning is a task of generating a text for an image based on the learned knowledge from the training set. And we have been using a set of samples excluded from the training set as a test set. But what if we don't have a designated training set or even the validation set, so that we have no idea of what these tasks are? So in zero-shot tests, in a literal sense, the model should be able to generate a proper captions for completely unseen image data set. Then the next natural follow-up question would be, what is such an unseen image or data? So since the test set can contain highly detailed descriptions for many other data sets, such as Wikipedia or emotional comments from Instagram posts or advertising copy and so on, a model should be able to cope with various concepts, styles, types, context of images or text. So since the target can be in the form of question answer, sentiment analysis, summarization, or even open-ended generation, a zero-shot caption model should be able to handle all kinds of different tasks. So since the workshop proposal, we have been trying to rethink about the future of zero-shot image captioning tasks, and we came up with one possible important direction. Is that truly zero-shot image captioning may require an input prompt. So to give you more context, I'll show some examples from our latest EXA1 multimodal model. First of all, a good model should be able to explain an image in details if needed, and also ask questions about, answer questions about the image. For zero-shot image captioning, we can also designate a style. For example, we can ask to generate advertising copy given the image. And sometimes we may even need a first draft or resume or personal statement given the image, or even the Instagram or other social media posts with hashtags and so on. So since last year, we have been thinking hard to find answers for what is zero-shot image captioning task and how can we solve it. Now we are developing an image captioning model that can follow instructions to perform a variety of zero-shot captioning tasks in a more flexible manner. So one of the key insights is that possibly a truly effective zero-shot image captioning may necessitate an input prompt to handle wide spectrum of images and text and tasks. Of course, this is not a final goal, maybe just the next step as a part of our journey toward better image understanding and also making it more useful. So hopefully there will be another workshop investigating these aspects in the next year. And thank you very much.
Questions? It didn't make sense to, I mean, the zero-shot image captioning. It didn't make sense. It didn't make sense to handle out of distribution image indeed. So actually, so the models based on some typical images, trained based on typical images, but is it really possible to handle all the data using the model?
So practically it may be very challenging, but at the same time, if we want to call it zero-shot, ideally we want to go beyond the training data. So I just wanted to raise a question.
All right, let's thank Hong Nam again. And in the nice workshop in CVPR 2023. Thank you.
Yeah. Okay. And we have to also take the 네.
Hey, hello.
Hello, yeah, we forgot to take your photo for the first place.
Uh-huh. Okay,
Yeah.
okay, okay.
Yeah, we're taking the photo.
잘안 보이거든요. 뒤쪽으로 이 얼굴만 안 가리고 이 프로젝트 뒤쪽으로 좀 올려주시면 형태가 보이겠습니다. 네, 좋습니다. 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 잠깐만요. 그 소감 좀 잠깐 짧게라도 한번 부탁드릴까요?
Could you say something how you felt or how proud of you how you are proud of yourself or could you say something? I'm sitting this Can you say something? Could you say something how proud of yourself or stuff like that?
Thank you for everyone.
Thank you. Thank you. Well done. Well done.
Thank you. You're good to go. Thank you.
Okay, okay, okay. Thank you. Bye, bye.
A picture. A picture all together. Can we put